Started. All right. And here we go. Trying to share my screen. All right. Can everyone see the screen right now?
Sure can.
All right. Thank you. Thank you. All right. So thank you everyone who is joining right now. This is Zenith Flight Readiness Review for 2022. We're really excited to show you all everything we've done this year and our presentation. So first, these are some of the things we're going to be covering. First, we're going to be talking a little bit about our SCR and AIAA, team overview, also an overview over Zenith, a little bit of the budget. And then we're going to be going over all the sub teams as you see down there. Each sub team is going to be talking about what they've done this year and what their role is with Zenith. And then at the very end, we're going to be talking about some takeaways and lessons learned, and then talk just a little bit about SCR next year. And then at the very end is when we're going to be answering all questions. So right now, we just want to get through the presentation, get everyone to present. And if you can just save your questions for the very end, that way we can make the presentation go by smoothly and fast. So SCR and AIAA. So if you don't know and you're just joining, you're not familiar with the AIAA. Space City Rocketry is just part of AIAA. We're one of their engineering teams. And the whole purpose of AIAA is just to increase presence of aerospace engineering at U of H. The mission is achieved through professional development of our members, providing a home for competitive project-based teams, and so on. So thank you, AIAA. All the offices work very hard to help our team succeed. Before that, let me also introduce myself. My name is Irvin Soriano. I am the project manager for Space City Rocketry for 2021-2022. I am now a graduate from University of Houston as a mechanical engineer. And now let me pass it on to Gustavo.
Yep. Hello, everyone. My name is Gustavo Santana. I am the chief engineer for Space City Rocketry this year. I'm also a mechanical engineering student, but I'm graduating in December. So I still got a little bit left, but you know, it goes how it goes. So a little bit about SCR history. The team was created in 2015 exclusively for the IREC competition. And the first time we competed was in 2018 with Prometheus. I know some of the members in the call were the ones who built that. So a huge shout out to them. And since then, we've been competing with Oberon in 2019 and 2021. And they placed very well. We placed first in Texas. And this year, we want to be more ambitious than ever. And we're going to be competing in the 30K COTS category with Zenith. Along the way, we've also been working on some other projects, some SRAD components for this rocket and future rockets. Notably, we've been working with fiberglass components made in-house, SRAD sensors for our avionics systems. And we've had some capstone teams working on mechanical separation systems for future potential two-stage rockets, oxidizer injection systems for a hybrid rocket, and some SRAD solid propellants.
Yeah, so now let's move on more of what the presentation is today and the things we want to achieve. First of all, we want to just get feedback and get approval from advisors like Randy and other alumni who are joining to make sure that we are on the right path to launch this June at Space for America Cup. We also just want to showcase all the work and the new implementations the team has had this year. There's been a lot of changes, a lot of things that we've done this year that we've never done before. So we want to present that to you. And then obviously, once you see everything we've done, we just want to provide some insight of where the team wants to head in the next few years and what we can accomplish. And then also just gain more support and expand awareness of the engineering excellence that the team provides at the University of Houston. One thing I do want to mention though today is that for today, we were expecting the rocket to be around 90 to 95% completed. However, because of finals, because of many of us graduating, our report, and just the ambition of us trying to pursue 30K in just 1 year, there are some notable things that have not yet been manufactured, but we do have a plan to finish them within the next week, and we'll be talking more about that. But yeah, let's move on to team overview. This is the way that the team is structured this year. So we have a total of 6 sub-teams. At the beginning of the year, we had 7. However, we combined 2 of them. But we are on the AIAA. As many of you say, we're just part of the AIAA umbrella. And at the very top, you have me, the project manager, Gustavo, our chief engineer. We also have our analysis lead, Ravi, our avionics leads, Raj and Josephine, our payload leads, Isabel, propulsion leads, Ozzy and Adrian, recovery lead, Carlos, and structures lead, Haley. We also have our EEE advisor who is joining us today, Randy Merrick. Thank you so much. And a few other mentors who help us out throughout the whole year. Whenever we have questions, they just want to advise. Right now, Space City Rocketry consists around like 50 active members. We did a really good job this year on keeping members involved and able to learn a lot. And this is just a little bit of demographics on the team. We do have a lot of majors that are part of the team, not just engineers who work very, very hard. And we just want to continue expanding on that every single year. So now let's move on more and talk about Zenith. Gustavo will be talking over more about Zenith, but before that, just a timeline. And last time we met with a lot of the alumni and the advisors was in our PDR in November. And we had a plan of finishing a lot of things in December and January and starting the manufacturing process. However, and as you will see later on with some of our key takeaways this year, due to us having low resources and not being able to do a lot of things we want, our design process, our validation process took a lot longer. And as you can see here in the redesign process, we were expecting to be done with that around mid of December, but it did take a lot longer, and we finished in January. So anything that you see in red is just how much longer we took than expected. At first, we were going to have a CDR around April. However, we decided just to have an FRR, Flight Readiness Review, which we're having right now. And then our competition is going to be taking place in June. And Gustavo can take over the design overview.
All right, so this is Zenith. This is the rocket we want to be competing with this year in the 30K COTS category. Zenith, as we're going to be competing, is going to be standing at 116 inches tall with a 6-inch diameter, coming in at 78.7 pounds. And we're looking at about just over 28,000 feet for our apogee. We're going to be including a boat tail, going to be using single bay dual deployment for our recovery system. We're going to be introducing a new component that is inspired by Randy's motor mount system called the modular lower assembly. We're going to have a carbon fiber airfoiled fins, and our propulsion system is going to be using an O3400 motor.
And then, as you can see here, we have a Zenith right now. We have already sent Zenith to IA Coatings, who are going to be doing our paint design, which you can see on this side right here. This is how we'll be looking. This is the O3400, and then you can see other components of Zenith. Now, one thing I wanted to talk about too this year is finances and how we started off and what we were expecting to do. Here you have all the initial budget that we planned on spending at the beginning of the year. And then this is the money we've actually received and we have accommodated for every single sub-team, the budget spent and the budget left. The slides will be posted and be sent out to everyone if you want to take a closer look at this. I just wanted to point out that at the beginning of the year, we did not start up with a lot of money. A lot of it came out throughout the whole process of fundraising throughout the whole year. However, we have managed to stay under budget. As you can see, some of the money we will be saving for next year. We have this how much Zenith is expected to cost, $5,400. Competition is going to be around $4,000. And we do, as I said, plan to save more for next year. But okay, it is time now to go through each sub-team and be able to learn more about Zenith and everything we've done. So take it over, Ravi.
Cool. Can everyone hear me okay? We good there?
Mm-hmm.
Great. Hello, everyone. My name is Ravi Desai, and I'm the analysis subteam lead for Space City Rocketry. Now, if you were familiar with the analysis subteam for Oberon, know that we have modified the subteam's goals and objectives from that mission. Previously, we were focused on implementing sensors to gather more physical data about the rocket during flight. But now, as we've transitioned over to the 30K COTS category, we were modified to help support this goal. And we saw this being possible through focusing on performing tests, simulations, and calculations. Most of our work will be categorized by some hand calculations, finite element analysis, computational fluid dynamics, some more flight simulations, and things of that nature. The main motivation behind this was to provide validation for design decisions. In the past with Oberon, we were able to certify that our systems worked because we were able to hold test flights, and we also had the 2019 competition in which we knew certain components would work. With the absence of a test flight this year, we found analysis to be extremely essential in providing that validation for these design decisions. So the work that we've completed this year will be expanded upon in other sub-team sections. So I'll be checking in throughout the presentation to highlight what we've completed.
What's up, y'all? I'm Adrian, one of the propulsion leads. I just graduated with a mechanical engineering degree, and I'm gonna let Robbie talk about the motor selection right now.
Thank you, Adrian. So analysis, in order to determine which motor would be best fit for Zenith, perform comparative open rocket simulations. We thought that creating a control configuration would be the best route in order to avoid a bias in data. We compared 15 different motors, 7 M class, 7 N class, and 1 O class. I do want to note that this was early in the design process. So this control configuration that you see on the screen was heavily based on Oberon. We did determine that the results of these simulations and analysis was still valid because the motor was still our largest factor of performance. So continuing on, we were able to simulate launches which each motor placed in the control configuration. We did make minor changes to airframe lengths and weights in order to standardize stability and ensure that the motor was the largest factor of performance. The analysis subteam determined that the N5800 and O3400 were the most viable options for Zenith. Ultimately, in the end, the O3400 was chosen due to its simulated apogee, its total impulse, and extended burn time. I do want to note that it has a 6.2 second burn time versus a 3.5 second burn time for the N5800. And this would decrease our max velocity and acceleration along with our drag force to more acceptable values due to that longer burn time.
And this is the Cicerone O3400. You can see some of its dimensions here and the thrust curve. As Ravi mentioned too, that burn time of 6.2 seconds is definitely one of the main reasons why we decided to go with this. And also its total impulse of 21,000. And now let's talk more about the open rocket flight simulations.
Sure. So the values you see on the screen are the open rocket flight simulations as we project Zenith currently to launch at competition. We're sitting at a stability of 1.5 calibers with a projected apogee of just over 28,000 feet. We project to reach a max velocity of around just under 1,800 feet per second, or around 1.6 Mach. Our max acceleration of 443 feet per second squared, or just under 14 Gs. We do have a launch rail departure velocity of 116 feet per second, which clears the IREC guidelines. And our time to apogee is projected to be 38.9 seconds. You can see a plot of our simulation in the top right, and then the layout of Zenith in Open Rocket on the bottom right. Now, we also employed the use of RockSim in order to get some more comparable values and not solely rely on Open Rocket. The stability did stay the same of 1.5, along with its mass of 78.7 pounds. We did notice that the simulated apogee was projected to be a bit lower at around 24,500 feet. The max velocity and max acceleration were comparable, although a little lower for velocity and a little higher for acceleration. The launch rail departure velocity is still above 100 feet per second per IREC guidelines, and the time to apogee is 36.5 seconds.
So here you can see the propulsion risk, and you can see that everything is either in the yellow or the green, which means that it's all clear. We have our negligible and probable thing being that the motor assembly taking more time doing due to it being O-class. We're not actually assembling the motor ourselves since it's it's O-class. We can't work on it, so I'll put that as improbable because we're not really the ones assembling that. The only seldom risk we really have is the igniter. So it's either an incorrect insertion of the igniter, which can be easily fixed, or failure to ignite the motor on the first try, which we can go again. So the most improbable thing would be Zenith reaching Mach 3, which would have some potential deviating or unfamiliar behavior. But as you could tell from the last slide, it only goes to, I think, 1.6 Mach whenever you looked at the simulations. Also, I'd like to give credit to Ravi and Tala for all the motor selection stuff. They worked really hard on that during last semester and everything.
Thank you, Adrian. One thing I want to point out too is that for the motor assembly, something that we used to do was we used to assemble our own motor with solid propellant. However, because of the new regulations from IREC, we can no longer do that ourselves. We opted out for the company Cicerone to assemble it for us at competition. Now it is structures.
Hi everyone, my name's Haley. I'm about to be a senior in mechanical engineering, so I'll still be here next year. Just starting off strong with the nose cone. We went with a 4-1 tangent O-give. The main things we considered while doing this through a trade study at the beginning of the year was the drag calculations that Analysis so graciously did for us, the price of the component, and the actual availability of it. We considered a lot of different options, but there are only a few of them that were commercially available since we weren't looking into creating our own nose cone just yet. And then this one just had comparable prices and availability to the other commercial ones. So the main difference here was the drag calculations, which I will let Rod grab on the next slide.
Thank you, Haley. So as she mentioned, Analysis performed the analytical component of the trade study, which we determined to be a drag force data analysis, once again, utilizing OpenRocket. We considered 7 total different nose cone profiles. You can see the profiles considered in the leftmost column of the table at the top. They were the 3/4 and half variations of the power series, the 3/4 and half variations of the parabola series, the full parabola, an LV hack, von Karman, and a tangent ogive. So similar to the motor simulations, we created a control configuration, this time much later in the design process, so we were able to get a more clear representation of what Zenith is like today. But we outfitted each of these control configs with a different nose cone and then simulated their launch. Instead of just comparing apogee as we did with the motors, we were able to analyze the simulation data from OpenRocket in MATLAB. And we were able to obtain drag values for each nose cone that experienced in the subsonic, transonic, and supersonic regions, as well as accumulating all of the total drags to apogee. I do want to note that particular attention was paid to the transonic region due to flow instabilities, and that led us to determining the 4-to-1 tangent ogive to be the nose cone profile best fit for Zenith.
So as far as the airframes and couplers, after playing around with different OpenRocket simulations, we decided to shorten the upper airframe that we had originally purchased. So that was shortened down to 25 inches. This just allowed us so that the payload and the avionics bay sat in a preferable area in terms of distance from the motor, just so we could hopefully play with our stability a little more. And then as far as the Can y'all hear me now?
Yeah, we can hear you.
Sorry, my mic's honestly pretty bad, so let me know if I end up going out again. So as far as the airframes go, the upper airframe was shortened just to make the payload and avionics bay closer to the motor, just so that would help our stability a bit more. The avionics bay is above the payload bay just because the recovery system is kept in the nose cone. So it's preferable to have the avionics system be directly in contact with that as opposed to trying something like going through the payload bay if it were to be in between them. So that was a determination for that. The bays were both used in Oberon, so they did have previous holes in them. So we decided to actually patch all the holes that were in the avionics bay, just so we could actually strengthen it up a little bit. We did use some reinforced epoxy for that. And then we also did an inner layup so we could go ahead and add some even more strength to it. Then we also added some flange nuts on the backs of all of them, just so the epoxy would actually have something to grab on. And so we have 9 and 12 in the avionics and payload for those. And the amount of screws was mostly determined from the screw calculator that Analysis created, which I believe should be on the next slide.
Sure. Thank you, Haley. So as she mentioned, for the avionics bay, we determined that 9 832 alloy steel hex drive screws were necessary. So when looking at how many screws we wanted to use on both the avionics and payload bay, we wanted to analyze what are the max points of stress that are going to occur on this system throughout flight. And thanks to Oberon's test flight, we do know that the max force usually sustained by these systems is the landing load. If you remember Oberon's first test flight down at the south site, we launched with plastic rivets securing our payload, and they survived launch perfectly fine. But as we landed, the payload was sent down our airframe and completely sheared all of our plastic rivets. So that was our motivation behind choosing the landing load as the most intense force. We also made some assumptions regarding this landing load and that 5,400 pound force value. We assumed that we were going to be landing on a pretty rocky and hard surface. So a deformation of only 1/4 of an inch of how far the rocket goes into the ground when we land was assumed. We also assumed a worst case scenario descent rate of the main parachute being 1.5 times its projected. So 1.5 times 30 gave us 45 feet per second for the main parachute descent rate if the cords became tangled. So from there, we were able to calculate the deceleration that the entire rocket experiences, and then calculating the force that will act on these screws as we land in this worst case scenario. So from that, our screw calculator gave us 9 total screws for the avionics bay and 12 total screws for the payload bay. Now, I do want to note that we have a factor of safety of 1 for our payload bay. It is assumed to be still good for flight, as we are making a pretty severe assumption with these landing loads, and that 17,000 pound force value is something we definitely do not project to occur at competition.
So the motor block was an addition that we made this year since we are securing the motor from the top as opposed to a securing at the bottom the way Oberon was done. So essentially we'll have this motor block sitting above the motor, screwing in with a countersunk screw into the top of it, and then it will be secured with 6 632 screws. It was determined that we wanted to go with aluminum 6061 T6. Shout out to Eason for machining that for us. During machining, it did turn out that we had an issue with tapping one of the screw holes. That one's actually an 832 screw, but it is still usable. And the design was also created by Eason, and it was manufactured earlier in January. The boat tail has been one of our big proud moments for structures this year. It improved originally we were thinking that we were not going to get very high on apogee, and so we were trying to find new. So for the boat tail, we ended up playing around with different things that we could do to improve apogee because we were worried we weren't going to get very high. This ended up adding a lot for us. The actual dimensions of it was determined by playing around with Open Rocket to see what would maximize apogee without being anything that was too ridiculous to produce. The dimensions of this are listed below. That was done using graphene enforced epoxy that IA Coatings cooked up for us. And we also used 4-ounce and 6-ounce fiberglass sheets. It took us a couple of tries, but we ended up getting a really solid piece created as of a couple of weeks ago. So this is just kind of verification of the improvement that we got from Zenith with and without the boat tail, as you can see. This was just validation for the previous apogee and the current now estimated. So I just wanted to talk a little bit about the boat tail process just to kind of discuss some of the things that we discovered. So we tried out different methods of securing and try to find sources online. We determined that PVA and mold release was the best forms to actually work with. We ended up using 3D prints, 2 half prints. For the lip, we ended up using the reinforced epoxy with graphene and chopped fibers to try and get a really clean lip on there. And then we just layered over with fiberglass sheets on top of that. Next one. And so by doing that, we ended up producing these 2 lovely negatives right here. We actually ended up having to do this process twice just so we could perfect the process, whether like a heat gun helped or how many layers do we need to do to make it strong enough so we could really perfect it. Once we had these 2 negatives, we were able to do the same process of doing the chopped fibers along the lip, as well as doing the inner layup after we had used the molds to screw into the sides to keep them aligned. So that way we didn't have an issue with, turns out the lip doesn't line up for both of them. Then we ended up cutting them in the leather stage, so we didn't have to deal with the Dremel too much when it came to the positives. And we ended up with this lovely boat tail right here, which ended up fitting perfectly. And we also did an outer layup to strengthen it even more, just because we noticed some imperfections on the edges where the 2 positive halves were combined. Another thing that we are working on is the MLA. I will say that we have all of the parts for this, but it has not been done yet. But as far as the layup process, it's going to be the exact same as the boat tail process. So we're very confident that we can get it done effectively in one try, especially since carbon fiber is a much more expensive material. For the upper centering ring and bottom centering ring, they're not necessarily cupping the fins as it looks. The bottom centering is actually cut into 4 quarters, and the top one is just kind of sitting on top of the fins. These are all components that are going to be a part of the MLA, which will be just the motor sleeve, the 2 centering rings, and the 4 fins. Next slide.
Yeah, so also just to add in, the MLA is an addition that we're going to be adding to the rocket, mostly because it's going to serve a couple purposes for us. One, it's going to allow us to replace the fins if they do break at competition, and that is a big priority for us, given that the fins were damaged in the 2018 competition with Prometheus, and we had the MMM, or the modular motor mount, for Oberon in 2019 and 2021. So we want to have this this design so we can replace the entire lower assembly to, 1, replace motors if need be, and fly in different configurations, as well as fly with different fins if they do get damaged.
Yeah, we also went with a design more similar to this just because of the strength behind it, just because with the MMM, we did have concerns about, tripling the apogee that it's going. We were worried about the divergence in the fin flutter, which we'll talk about later.
Sure. So analysis was also employed to use a screw calculator to determine how many screws will be necessary for the modular lower assembly. In the end, we determined that we need a total of 12 1/4" 20 alloy steel hex drive screws. We also determined that 8 screws should be placed on the lower centering ring, which Haley mentioned is divided into 4 quarters, and 4 screws used on the upper centering ring. This was determined with a factor of safety of 1.41. And the predicted landing load was with the same assumptions made from the avionics and payload bays. Something I forgot to mention is that we assumed a worst case scenario as if Zenith was landing like a pencil straight down. And as the MLA will be the first point of contact if that scenario does happen, that's what gives us this extremely large predicted landing load of 30,000 pounds force. But these 12 screws, according to our screw calculator, will be able to hold up against those projected forces.
I'm going to make a note really quick that we're not ignoring all of y'all's questions. It's just we're saving to answer all the questions at the end of the meeting. So we will get to everything. Just make sure to re-ask them so don't forget them.
Yes, so we were also able to run some finite element analysis on the modular lower assembly. So as I just mentioned, the worst case scenario landing load of 30,000 pounds force was applied to the bottom where we project the force to impact. We were running these simulations in order to verify load distribution across these fasteners. Before we ran these, we previously thought that the load would be evenly distributed amongst all screws or all fasteners of the system. But after running these, we were able to see that there is actually much more of a concentrated load on the bottom centering ring due to it naturally being closer to the impact force. And each fastener in the bottom centering ring experiences around 3,400 to 3,700 pounds force, while the load drastically decreases for the fasteners in the top centering ring to 380 to 400 pounds force. So this was also able to give us a reasoning behind using 8 screws on the bottom centering ring in order to better distribute the load and also not be able to add too much weight to the aft end of Zenith.
For the fins, we went with 4 carbon fiber fins. The main reason for this was, as I said, the fin flutter and divergence. We were dealing with a lot of calculations for that. And once again, we're unfamiliar charted territories for the 30,000. So we were heavily focusing on that, which is why we also amped up the thickness to 0.315. A lot of the dimensions were heavily based on the center of adjusting the center of pressure because we wanted to ensure that stability was going to look nice for us. And in doing so, we ended up having to beef up the fins. We also went with this tapered edge to help us with the drag. There was an issue during machining as far as one of the tapered edges. And so we've also been working on cleaning that up using some chopped fibers and some epoxy, trying to use the straight edge so we can get a very comparable match with the other fins. And then, I mean, I guess if you'll remember, these will also be attached. So that straight line on the edge will also be attached to the MLA.
Sure. So as important as ever, we did want to make sure that our fins would not flutter or diverge. And in order to do this, we utilize the program AeroFinSim for these calculations. Instead of assuming the regular carbon fiber input it has listed as a material on the program, we were able to gather material properties of the carbon fiber from the vendor and use those to give us a much more accurate representation. I do want to note that our max velocity of Zenith is projected to be around 1784 feet per second, occurring at roughly 7,000 feet. This is in line with the critical velocities for both divergence and flutter, which are listed at around 2,200 and 3,500 feet per second. So we are clear on those with the fins.
So as far as risks, part of the main concern was the actual landing forces, but also the forces experienced during flight. As of right now, our most critical one would be failure of the rail buttons or the motor block or fin flutter or divergence. Main reasons for this is failure of rail buttons coming off the pad would be very dangerous as we would have no real direction or control of the direction. If the motor block fails, we have an entire motor falling out the back of the rocket. Probably not ideal. Fin flutter and divergence, as Robbie was saying, it's a very critical point and it can completely mess with the direction, the apogee, really anything about the flight. Something that we considered critical but also improbable was the fastener hardware failure or improperly mounted fins. This is not an assumption that the fin is going to fly off the rocket, but instead an assumption that maybe they are epoxied too crooked, in which case it may cause some sort of a spin or just may mess with the flight. And for fastener hardware failure, that also kind of applies to more so the landing forces, and that's where we're expecting to see the most forces. So that's just the hope that it would still be reflyable after, and that it would be something critical but not completely catastrophic. For moderate and seldom, we're making the assumption that if there is damage to the fins or the airframe or boat tail, that they're happening during landing, but we're expecting that maybe there may be a slight crack or something that may just need to be fixed up a little bit, but not where it's completely shattering. And we're predicting that that would be a seldom occurrence, as there's so many factors that come into it that we just want to acknowledge that. And then since IA Coatings is so graciously giving us a beautiful paint job, we have our occasional scratching of the paint, which is negligible.
Thank you, Haley. One thing I want to clarify right now is that you might be asking why we don't have a thrust plate. The MLA serves as kind of our thrust plate this year. It will be taking on all the load from the motor. The reason why is we weren't comfortable with having a thrust plate in our boat tail, which we just started working on this year on taking all that load. That's why we went above and beyond on choosing what size screws, the thickness of the MLA, and so on. But if you'll have more questions about that, again, as Haley mentioned, we'll be answering them later after we complete the presentation. But now let's move on to payload.
Hi, everyone. I'm Isabel. I'm a junior majoring in biology and environmental science, and I'm your payload lead. Our overall objective of Zenith's payload is to observe how accelerative and gravitational forces, as well as the pressures of spaceflight, affect E. coli and their reproductive behaviors. We're trying to answer two major questions, which is how do the pressures and accelerative forces of spaceflight affect the reproduction and growth of E. coli? So when you're looking at our two hypotheses, which is the null hypothesis, the expected hypothesis within the scientific method, it's the opposite of what we're asking. So it's the internal pressures throughout Zenith's launch will not affect the reproductive behaviors. Our alternative hypothesis, which we are asking and trying to figure out, is the internal pressures throughout Zenith's launch will affect the reproductive behaviors of E. coli. These hypotheses are important as we'll analyze them later on when we get our results. Our second question is, will the pressures of flight decrease the growth rate of E. coli? So our null hypothesis states that during Zenith's launch, the E. coli will maintain an ideal exponential population growth rate of y equals a times 2 to t over 20, which I calculated because E. coli doubles every 20 minutes. So 2 is our growth rate, and then time would be minutes divided by 20. We can also convert that to seconds if needed, and then A is the initial amount of E. coli that we have starting. And then our alternative hypothesis is that the population growth would be less than that, as it would decrease due to pressures. Our results will be applied to studying infectious behaviors in and the gastrointestinal health of astronauts, as E. coli is found in the intestines, which I can elaborate more on in the next slide. So E. coli stands for Escherichia coli. There are different classes of that. However, the two main ones that we looked at when trying to choose a strain of it was commensal E. coli and UPEC, which is uropathogenic. Uropathogenic causes a lot of infections, common infections within humans. So although we're using commensal E. coli, which is the more harmless one, so in case of bacterial contamination, there are no major infections caused. If this strain theoretically were to mate with other strains, that would cause infections. So we would be able to see how the bad E. coli can cause like incubation periods within like changes of pressure of the spaceflight. And then we would also see how commensal E. coli grows and takes up resources within the gut microbiome as the pressures change. It reproduces at fast rates. Like I said, it doubles every 20 minutes during the exponential phase. So the chart on the right is a averaged curve of all bacteria. It's pretty accurate to E. coli. So there's a lag phase for the first hour and a half. And then we do have a few hours of the exponential phase. And then the stationary phase is when the growth kind of dies off and they take up too much of the resources to grow further. And that protects us from any other bacteria trying to cause infections. It's also not oxygen dependent and it's temperature resistant. So within that, it creates a better like observation for us because those factors it's not dependent on those factors, which means the forces and the pressures would be the only thing majorly affecting it. And then it's also gram negative, so it can be stained pink to be able to see better with the camera. I'll be culturing it on a McConkey nutrient agar plate. With that, it measures the lactose fermentation of that. So gram negative bacteria will come up red. If there's any chance of us being contaminated with other bacteria, that bacteria will not come up red. So the E. coli will be isolated and seen better, and it'll save us a lot of time trying to figure that out. It'll be swabbed on a 60 millimeter sterile glass Petri dish. So hopefully no contamination. For our camera, we're using the GoPro Hero 5 Session. Our ideal recording is 1080p at 60 frames per second. The sensor size is 1/2.3 inches, and the aperture is f/2.8. Our main concern with the GoPro was overheating. As it overheats, it could die faster, it could skip around, it could crash. So to mitigate that, we have a power bank that'll be hooked up to give extra battery life to, and then heat mitigation, which will be explained in our cooling system later. So when it comes to our magnification system, we mimic a traditional microscope model. So we stack the lenses at certain apertures, focal points, and measure the refractions of everything. So we do 10 times magnification macro lens with a 40 times magnifying glass to reach 400 times magnification. The way it's set up is our light source is on the bottom, and then our Petri dish, and the light source goes to the Petri dish, and then the lenses are stacked and the camera sees through those. So our light source beneath the Petri dish is at an angle giving alpha equals 30 degrees, which will be used in the numerical aperture of the lenses. So in the next slide, I'll elaborate more. So the numerical aperture of our bottom lens can be calculated by doing n times the sine of alpha. So the sine of alpha would be 1/2. And then n, our refractive index of agarose, was measured by taking the sugar and salt contents and measuring the percentage of that against the water in our agarose, which gives us n equals 1.335. We would multiply that by 1/2, and that would give us our numerical aperture of our bottom lens, which is 0.6675. And then as it states, it's equal to the diameter of the bottom lens divided by 2, divided by our focal length, or our focal point at the bottom. So the diameter of the lens is 25 millimeters, which then comes down to 12.5. And we use that to figure out the focal point of the 40 times lens at the bottom, which is 18.73. And then the second figure on the right is how we proportion that to get our 10 times focal length of 4.68 millimeters. And that's how we will stack the lenses at those distances. For our structural components, we have the CubeSat of 10 centimeters, 10 centimeters, 10 centimeters, 30 centimeters. It'll weigh 8.8 pounds. We have our ballast. We have stabilizers, which are rubber washers and rubber grommets between a lot of our hard equipment, and then foam to dampen more vibrations. We have our steel frame. The steel gives structural integrity and dissipates heat from the inside, acting as a heat sink to further take away heat from the GoPro. And then we have our 4 zinc rods that are 1/4 by 20 that run through the payload bay that everything is secured on. And then our headlamp sits at the bottom. Within the steel frame lies the spacers that are cut to the focal lengths that we wanted. And then our mounts holding all the components, we refer to this as the internal frame. The mounts and spacers are printed out of standard PLA. There was cause for concern that the heat could mess with the structural integrity of our mounts. However, after doing a trade study on 5 other 3D printing filaments and a series of heat chamber tests that went up to 200 degrees Fahrenheit, we concluded that PLA had the best attributes and was the most available. And it's only going to get up to like 115 at the most extreme in New Mexico, so we should be okay. For our payload cooling system, our purpose was to prevent overheating of the camera and the power bank. So what we're doing is taking instant ice packs, which is ammonium nitrate and purified water. When that salt is dissolved in that water, it creates an endothermic reaction, which makes it cold. It sucks in all the heat. So it'll fit within the X's on the right. Those are each calculated to be 36.823 cubic inches. As we tested it in the heat chamber, they could stay cold for up to 5 hours. That thermometer on the right measured it after coming out of the heat chamber for a good 30 minutes, I believe, and it was still cold. I have a base proportion of 30 milliliters of water plus 3 grams of ammonium nitrate, and that approximates about 2 cubic inches, and we can mess with that proportion to create stronger solutions, and then also to fill in the other cubic inches. We also have space above the payload frame to add an extra cooler to keep the GoPro cold. And as the solution is shaken more and mixed, it will become colder, so the vibrations within the rocket will hopefully maintain the coldness. And then for our expected results, it's inferred that the reproductive behaviors will be affected. What we plan to do is compare the recorded footage against the pressures measured by avionics. As we calculate the surface area across each frame per cubic millimeter, we can create and simulate an observed growth curve using statistical code on RStudio. As we do that, we will compare our observed and our expected values with a chi-square goodness of fit test. As you compare those, you'll get a p-value. If the p-value is less than our critical value chosen of 0.05, we can reject the null hypothesis, meaning that we are correct and it does affect reproductive behaviors, and it also decreases the growth curve. And if it is over 0.05, then we fail to reject that, meaning that our experiment could be inconclusive. So this is just a way to further confirm that we got accurate information. So for our payload risks, we kind of went with anything and everything that could happen and go wrong, just because we didn't have it in the PDR. But for negligible and improbable, we had condensation over the Petri dish and the camera lens, which we will be spraying everything with hydrophobic spray as much as we can so that the condensation will dissipate from that. And if it does happen, it will not affect us, our data collection too much. For minor, we had devices get wet and the charging cable falls out of the plug for improbable. And then for moderate and occasional, we have internal frames crack because a frame from last year did crack. However, it did not affect the performance of the payload at all. And then the internal frame mounts is improbable due to our cooling system and the heat resistance of PLA. Under critical, we have bacterial growth curve, not an exponential phase. It's seldom because the specific one we're doing, we can time it due to it being freeze dried, and then we will rehydrate it at the right time, right before competition to come out and time those phases as they launch. For improbable and critical, we have the instant ice packs leak. Because the ammonium nitrate is a skin irritant, it is very critical if these do open. However, it is improbable as we make them. The plastic is very durable and there won't really be anything in there to pierce it or burst it. For catastrophic and seldom, we have electronics overheat and fail. That was seldom because it did happen last year. However, they did not think of heat as a factor, like a risk factor for this. So we have been trying to mitigate that. And then catastrophic and improbable is bacterial contamination. Bacterial contamination definitely won't happen because the petri dish will be secured, but it would be catastrophic if it did happen.
Thank you, Izzy. All right, now it is avionics.
Hello, everyone. My name is Raj Kohil, and I am currently a freshman mechanical engineering major at the University of Houston. I'll be turning a sophomore next year, and I am the co-sub team lead for avionics along with Josephine. And today we're going to present you all the work that avionics has done this year. So just a brief overview of avionics. So our job is mainly to create electronics that detonate charges and collect telemetry data. We also have employed both a COTS and SRAD system this year with flight computers on both. We have also created a portable ground station to view live data while the rocket is in flight from our flight computers and sensors as well. And ultimately, through GPS tracking and other methods, we provide critical information in locating and recovering the rocket. So you can see here to the right, there's our sub-team at a social. Our team has grown exponentially large this year, and as a result, we were able to work on a lot of both COTS and SRAD projects this year to expand our avionics system. So on the next slide, this year, avionics was divided into two systems that we are working on, so two major projects. First, we have our COT system, which is mainly powered by two flight computers, our primary flight computer altimeter, which is our telemetrum version 3, and our redundant flight computer, which is our Easy Mini version 2.0. We are also using an SRAT system, which is new to us this year, in which we are using a portable ground station to view live data, which is powered by a grounded Raspberry Pi Model 3B+. And we also have an SRAD Sensors flight computer, which is a Teensy Arduino 4.1. All SRAD flight computers do not ignite any charges. They're simply there to view and collect sensory data and report it back to us. So first up, I will present COTS avionics, and then my co-sub team lead Joe will present SRAD avionics later. So moving on to the next slide. We have COTS avionics. So first up is our COTS flight computers. So just to give a quick rundown before I go more in depth, we're employing two COTS flight computers this year for Zenith. Our primary flight computer is a telemetrum version 3, as I discussed earlier, in which the charges it will release on its main and apogee terminals are the tender descenders at 1,000 feet and CD3CO2 system charges at the drogue. And it has a built-in GPS sensor to track and recover the rocket, as I will talk about later. And it's currently powered by a 3.7 volt, 25 milliamp per hour LiPo battery. And as for our backup redundant flight computer, we have on our, as you can see here on the right, the Easy Mini version 2.0. It currently ignites the black powder charges as a backup charge to ignite at apogee with a 1-second delay. And it also releases tender descenders at around 800 feet, as I'll discuss later why we chose that altitude. And it's also powered by a 3.7 volt, 25 milliamp LiPo battery, as milliamp per hour LiPo battery, and both flight computers have general sensor data. So they output pressure, altitude, temperature, speed, velocity, and acceleration data. So on the next slide, to go into more depth into our primary flight computer, it's a Telemetron V3.0. It has dual deployment supports with microsensors, so it has onboard non-volatile memory. So what that means is that as it's data logging all its data, even if it's not powered, it will still save that data onto a micro SD card. And it also has onboard live data logging. So as the rocket is being launched, on our ground station, we'll be able to view live telemetry data. And it also has a barometric pressure sensor with a built-in Kalman filter. So it works about to 100K feet. And it also has a 1-axis 200G accelerometer. The telemetrum also has an onboard GPS, in which the way it works is that right before we launch, we will put the telemetrum in monitor idle. We will let around 4 satellites lock onto the telemetrum, which will then allow us to get map data. And then after that, once we launch, we'll be able to recover the rocket, as we'll see on a map, the GPS location of the telemetrum once it's landed. So the way we transmit that data is for a 70-centimeter ham band transceiver for the telemetrum, in which you can see on the top right of the picture on the right, there's a black antenna soldered onto the telemetrum. Through a teledongle, which we'll get into more in depth later, we'll be able to access that data with a technician level ham radio cert, in which both me and Joe, as sub-team avionics leads, and a few avionics members this year have managed to get after doing a ham radio test, and we both all are ham radio certified. So we are certified to activate and access those radios. And it currently uses a 3.7 volt LiPo battery, which with its milliamps per hours lasts about 8 to 10 hours, which is more than sufficient for our primary flight computer. And its dimensions are about 70 to 25 milliliters with a weight of 17 grams. So on the next slide, we have our COTS redundant flight computer, which is an Easy Mini version 2.0. It also has dual deployment support and capability as well, with an onboard non-volatile memory and onboard data logging. While the Easy Mini redundant flight computer doesn't have any live data logging, which means we won't able to see it in real time, it will save all the data for viewing later after launch. And it also has a built-in barometric pressure sensor with a Kalman filter, and it uses any battery from 3.7 volts to 12 volts. However, the reason why we opted to still use the 3.7 volt 25 milliamp hour LiPo battery as well is because any type of 9 volt batteries tend to discharge fast and have a low battery life and aren't the best for flight computers. So that's why we opted to still use the LiPo battery as well. And its dimensions are around 38 milliliters by 20 milliliters, and it weighs at 6.5 grams. So on the next slide, you can see on the left, we have our wiring schematics. So you can see how exactly we connect our charges to the E-matches and how we connect it to the terminal blocks and to eventually to our pigtail connectors. And as you see here on the right, that is our almost finished full avionics tray. While we still haven't worked out some kinks with the battery holders and the LiPo batteries, we are very confident we'll be able to get the screw terminals and all the brass inserts completely finished and screwed in right before launch. Should take about a couple of days or so. But other than that, pretty much our avionics tray is finished. And we'll go into more into depth in the next few slides about our avionics tray. So you can see here with our avionics tray design, we have a 12-inch coupler with an 11-inch length tray. The way we have designed our tray this year is that we have a COT system on the front, and any SRAD components that go directly on the rocket, they will be attached to on the back of the tray. So you can see here on the bottom left, we have our 6-inch diameter airframe, and in it is our 5.75-inch coupler, in which it will holster our avionics tray. You can see here on the diagram as well, the coupler is about 5.75 inches, and we managed to place where exactly we want to place our terminal blocks and how they connect it as well. And the tray is held by a bulkhead with 2 threaded rods that go through the ends of the tray. It also has 2 pigtail connectors on the bulkhead as well, and 2 terminal blocks 4x2s. These terminal blocks will help connect our charges and our igniters directly from our flight computers all the way to the charges themselves. So on the next slide, you can see here that on our last slide, we had an orange tray, which is our prototype tray to mess around and figure out how exactly we want to place our components. And this time we actually redesigned our tray, as you can see on the peak tray to the right, in which we have our COTS components, which includes 2 4x2 black screw terminal blocks, 2 stacked battery holders, which will hold our LiPo batteries, a screw switch holder, and a 3x4x5 millimeter brass inserts with M3 screws for any holes to holster all our components. We also use plastic standoffs as well for both the Izimeter and the telemetrum in order to allow sufficient space as breathing room for the components that are at the bottom of these devices. And so the way we redesigned this tray from the initial one is we transitioned to bigger LiPo batteries for longer battery life, and to ensure that as well. And we also moved the terminal blocks to be vertical instead of horizontal like past years. The reason why we have this horizontal alignment is that the way that the E matches would come out through the sides, and that way it would not interfere with recovery's U-bolt design. And the screw switch is located at the bottom this year to not interfere with the airframe structure. As the way the airframe is cut, it would interfere with the cuts if we were to place a screw switch in the middle of the tray. So we opted this year to put it at the bottom. And so as for planned tests this year, avionics testing, our first test, we performed main two tests this year. Our first test was pressure testing. So for the COT system, avionics performed 3 pressure tests to gauge capability and performance of the primary and the redundant altimeters, and also test out their Kalman filters and how that algorithm works and see how well it works as well. So the way pressure testing worked is that we placed the altimeters in a vacuum lube sealed pressure chamber, and we pressurized the chamber from 14.9 psi to around 4.8 psi. And then eventually we depressurized the chamber back to ground level air pressure. The way this works, as you can see here on the chart to the left, is that pressure mimics the altitudes of going from 0 to 30K feet. And ultimately, the way we want this pressure testing to work is that we want to test out the ignition of the drogue and main terminals of both the primary and the redundant flight computers with Christmas lights and LEDs. So the way it works is that once it hits a certain pressure, if it detects apogee, the lights will light up, signifying that the charges have been ignited and that is igniting at the correct altitudes. And so for the easy meaty redundant altimeter, there is 1 to 2 second delays for both the main and the drogue / apogee ignitions, so that, and to ensure redundancy, and also to ensure it doesn't ignite at the same time as a primary flight computer. So on the next slide, we have our pressure testing results. So you can see here from the left to the right, we performed 3 pressure tests total. However, the first 2 failed as the pressure chamber had manufacturing defects and depressurized too quickly and just had a lot of issues. However, this result you see here is a result of our 3rd pressure test, which is successful. You can see here on the left and the right, our pressure testing reached an apogee for both flight computers at around 29.5K feet, which is a little higher than our initial apogee. However, it's the best results we could get. As you can see here, the data seems to be nominal. The only difference is that the temperature for the Easy Mini seems to be differing with the temperature on the telemetrum at around 10 degrees Fahrenheit. So because of that, that's why we opted to use SRAD temperature sensor, as we'll talk about later, in order to provide data validation and get more accurate results. So you can see here on the next slide, you see the pressure sensors, just average data for the pressure sensors for both flight computers and average data for the temperature sensors of both flight computers. On the left, the pressure versus time graph seems to be nominal and seems to have a smooth curve. So what that tells us is that our Kalman filter is working properly and ensuring a smooth curve and also getting rid of any inaccurate data and errors as well. However, on our right, our temperature and time data seems to be rather skewed and rather just straight and does not update correctly. So it only reads data of up to about 0.1 decimal places correctly, which isn't the most best data for us to use. So that's why we opted to use a more accurate and refined SRAD temperature sensor, as we'll talk about later, in order to provide data validation in order to get more temperature results accurately as well. So on the next slide, to go into more in depth of how apogee and main release, both altimeters read apogee at exactly the same time. There was only a difference of around 20 to 30 feet or about 10 to 9 meters, which is pretty accurate for both sensors. The redundant altimeter releases drogue and apogee 1 second later after it reads apogee in order to provide redundancy. So both flight computers read apogee at the same time. However, the Easy Mini reads the apogee, waits 1 second, and then releases the ignitions for the parachutes. And so as for the main terminal for the telemetrum, I think released at 960 feet for the primary, and then 920 feet for the Easy Mini. However, these seem to be really close ignitions and could be really could be really dangerous as for making sure they would ignite at the same time. So we adjusted the input delays from 900 feet to 800 feet to avoid same time trigger. And that was it for pressure testing. So for our battery testing, we also have avionics, also tested 4 LiPo batteries with capacities ranging from 400 and 900 milliamps. One battery is believed to be dead, and avionics verified that with testing. We can see on the left, we have all our graphs and our pictures as well. The experiment was designed to track voltage as the batteries charge and discharge. As you can see here, our 3 of our batteries are around 0.5 ohms on average, and the dead battery had 17 ohms. So in the future, if we want to test out other batteries and see which ones are dead and alive, you can see here on the left, this is the way of the future, how to test our batteries in the future as well, in order to ensure a more accurate voltage and current as well. So that's it for COTS avionics.
Hello, my name is Josephina Arguello. I'll be going over the SRAD flight computers, or the SRAD objective. So for the SRAD flight computer overview, the SRAD flight computer focuses on monitoring the rocket throughout its flight at all stages: pad, ascent, apogee, drogue, main, and landing. Its main objectives are to measure atmospheric pressure and acceleration, GPS tracking, and it logs flight data on a 32 gigabyte SD card. It's power supplied by a LiPo battery through the buck boost converter, and it's placed on the back of the avionics tray. So it's behind the primary and secondary systems. Please note that the SRAD flight computer is completely isolated from the rest, and it will not be connected to ignition or separation charges per IREC rules. Next slide. The flight computer Team Z 4.1 is our tertiary flight computer. It has a CPU power of 600 megahertz. It was selected due to its size, versatility, and has a built-in memory storage. The barometer was selected because it can be used in either I2C and SPI configuration. It has a 3.3 volt regulator, and it can be used with a 3 volt or 5 volt logic microcontroller. The accelerometers were selected because they have a low power consumption, and it can be used in either SPI or I2C. Next, please. The GPS breakout was selected because it has a built-in data logging, RTC battery included, ensures real-time tracking, and it has, and it's basically our redundant GPS. Oops. We did testing. Testing was conducted on the GPS breakout on campus. We confirmed that 3 or more satellites could not be logged on by telemetrum. We did this and ensured by moving the device around to make sure that it did not cause the lock to break. The XBE is a device used to transmit data in real time. It works alongside the Yagi antenna. Next slide, please. All right, the ground station. The ground station focuses on data collection. It reads off and receives data. So it's designed to interface with the COTS and SRAD system on the rocket. It operates on a Raspberry Pi. It has a touchscreen display, and we installed Altus OS. It's powered by a LiPo battery, which is capable of operating for several hours. We also added a toggle switch wire to conserve power consumption. Next slide, please. The Raspberry Pi 3 has 4 USB ports. We made sure that it was going to be able to operate in the average environment that we expect to see in Arizona. That is to say that the operating temperature is between 0 to 50 degrees Celsius. We downloaded Raspbian OS, which is a Linux distro, onto the SD card. Prior to this, we tried to download Ubuntu, which is another Linux distro. However, it was giving us error issues. Because of this, we decided to change to Raspbian, which gave us easier access to Altus OS. It also has external USB ports, which causes for accessible, easier access to charge the battery or adding an external battery pack to increase runtime. The ground station display, it's a 7-inch touchscreen. It's Raspberry Pi supported. It has screen dimensions of 194 by 110 by 20 millimeters. It has screen resolution of 800 by 480 pixels. The reason why we selected the screen was because of its ease of navigation between screens. We also selected it because it has no need for a physical keyboard or mouse. Its colorful display helps us utilize the gyroscopic data sent from the flight computer to show a 3D model of orientation of the rocket in real time, as the rocket is in flight mode. Next slide. Okay. The ground station telemetry system is uses APRS, which is a ham radio feature that shares GPS location. We did telemetry testing conducted each time pressure testing was performed. Range testing conducted at EEE with a nominal RSSI value of -30. The Alt-OS software that we installed on the ground station communicates with the telemetrum via the teledongle, which is then connected to the teleBT, which is connected over Bluetooth. The 3-element Yagi antenna, as you can see on the bottom left, it's the little purple antenna. It operates at 435 megahertz in 70 centimeter ham radio band. It is able to receive transmission throughout the flight, and it's capable of sending commands to the rocket for testing or troubleshooting. Next slide. This is the avionics risk diagram. As you can see here, we did our utmost best to make sure that none of the consequences were in red. Some of the consequences that we have here are unknown GPS coordinates, single misfire, none fire from a flight computer, LiPo battery connector breaks, broken flight computer, loss of GPS connection, location, and dead battery pre-flight. We ensured that most of these consequences were going to be in the improbable likelihood. For instance, the broken flight computer, we ensured that this was something that was going to be improbable by making sure that both flight computers, both COTS and SRAD, were going to be in protective cases that had foam on the inside to ensure that if anything were to happen, for instance, if somebody were to drop something, there would be no damage in transportation. Thank you.
Thank you, Joe and Raj. Now let's move on and go over our recovery system.
Hello, everyone. Can you all hear me? Good. All right. I am Carlos Soriano. I am the recovery lead. I am a graduate mechanical engineer. So let's get right into it. So the first thing is single bay dual deployment. Now, the reason why we decided to go with single bay was for the reduction in equipment and weight. And this semester, we have worked on validating all of our components as well as implementing the advice given in last semester's PDR. So the main parachute is going to be kept in the bag until we reach an altitude of 1,000 feet from the ground. And once this altitude is reached, the drogue is going to serve as a pilot chute to deploy the main parachute. And one additional detail is that because we're using the tender descenders, there is no overlap between the drogue and the main parachute at any stage during flight. Next slide, please. So looking at the parachutes and cords, our main focus with the parachutes was maximizing performance to reduce weight and volume of the equipment. And to look at all the different options, we used a calculator. Big thanks to Randy and Dominic for giving us the appropriate formulas to account for the impulse load and helping us develop the calculator. So you can see there on the top, on the right, you can see the formula that we use to calculate the impulse force, and then to calculate the terminal velocity, you can see it underneath. And then the first table is the different options that we consider for the drogue parachute. You can see that we input the coefficient of drag and the diameter of the parachute, and then it output the descent rate and the snatch force given the weight of the rocket and the air density during the deployment altitude. For both the drogue and the main, we decided to go with fruity chutes. The main reason is that they have really high performance parachutes with high coefficients of drag. And for the main parachute, they were the only vendors that we could find that were compatible with the configuration we're trying to go with the tender descenders, because they have a loop or a link on the top of the main parachute. So for the drogue parachute, it is deploying 1 second after apogee, and we are meeting the IREG guideline of having a descent rate of between 75 to 150 feet per second. Our expected descent rate at apogee is 125.44 feet per second. which will slow down as we get closer to the ground. The impulse force for this is 41.25 pounds. The parameters that we use for the calculator were a deployment velocity of 36.21 feet per second, assuming a 1.5 second free fall and an inflation time of 2 seconds. Now, upon doing research, we found out that if you are falling at terminal velocity, it takes around 2 seconds for the parachute to open. So that's why we went with a 2-second inflation time. For the main parachute, we are deploying at or near 1,000 feet above ground level. And same thing, we made sure that we were meeting the IRA guidelines of having a descent rate less than 30 feet per second. Our estimated descent rate for the main is 23.36 feet per second. Our impulse force for this is 276.17 pounds. This is assuming that we are deploying at 125 feet per second, which is the drogue descent rate, and having in worst case inflation time of 2 seconds. As you can see, all of this information has been tabulated on that table there. And that yellow and black parachute, that is the drogue, and the red and white one is the main. And then the last picture on the right there is that link that I was referring to before. The reason we needed that is to achieve the single bay dual deployment with the tender descenders. Now, for the parachutes and cords, we decided to go with Kevlar, and the reason for that is that it allowed us to minimize the amount of bulk and the weight associated with the cords. Once we knew that our maximum load of 276 pounds, we were able to consider different options using Kevlar, but we decided to go with Apogee Components Kevlar. They have a 1,500 pound Kevlar, which is what we're using as the cord to attach both the main and drogue parachute. And then we have one remaining cord that would be 300 pound Kevlar that's going to be used for attaching to the nose cone. And we'll see some figures of the whole configuration in a couple of slides. We did test the Kevlar with a 305 pounds load. This is because when we first got the cords, we thought they looked too skinny and we didn't trust it. So we tested it with 300 pounds and there was no signs of deformation or damage. Next slide, please. Similarly, for the quick links and U-bolts and swivel links and all that, once we knew our max load, we were able to narrow down our selection. So for the U-bolt, we have a 5,000 pound working load U-bolt and a 10,000 pound braking load. And then for the impulse bearing quick links, that means the ones that are going to be attached to the drogue and the main, we are using quick links rated for 900 pounds. And then for the ones that are not gonna endure any load, that being the one for the nose cone, is going to be a 400 pound quick link. Next slide, please. Now, our primary ejection system, to attach the nose cone and the upper airframe, we're using 3 440 shear pins. Each of them requires 40 pounds of brake. So if we're using 3 of them, that's 120 pounds. And then we are providing an additional 10 pounds to ensure they break, which brings our total separation force to 150 pounds. Now, the CD3 works by keeping a small amount of black powder in a pressurized chamber that's connected to an E-match that's connected to the flight computer. And then once you want to deploy separate the airframe, the E-match is ignited, it pressurizes the inside of the chamber, which pushes on a puncture piston that then punctures the CO2 canister and pressurizes the inside of the recovery bay. Now, the reason we decided to go with the CO2 system is to reduce the risk of failed black powder ignition, but it does come with some increased assembly. And to determine the size of the canister, we used a calculator that takes into account the geometric properties of the rocket, and then we input our separation force, and we take into account the gas properties of black powder of CO2, and then that gave us a CO2 charge size of 6.3 grams, but the smallest one we can use is 12 grams, so we're going with 12 grams. And then our secondary ejection system is a high altitude black powder charge. This was provided to us by Randy. So another big thanks to Randy for letting us know about this. But the way this works is that we take black powder and we place it inside of a centrifuge tube, which is then compressed by wadding paper to the top and then sealed with vinyl tape at the very top. And then at the bottom, there's an E-match that's epoxied in there so it doesn't come loose. So the reason why it's kept in this container is to provide a little bit of back pressure to ensure that the black powder burns completely regardless of altitude. It is really simple to assemble, and then similarly, we use the calculator to determine how much black powder to use based on our separation force, the parameters of the geometric parameters of the rocket, and the gas properties of black powder. So given that, it gave us 1.48 grams of black powder required for separation. Now, for the tender descenders, the way they work is that they allow the redirection of the tension caused by the parachutes by cutting a connection. And you can see there on the bottom picture, the whole assembly for it. But the two quick links shown on top are held together by the retainer, and it all fits inside of the housing. So there's a little bit of black powder and an E-match attached to the housing that when it's ignited, it pushes the retainer assembly out of the way, which prevents the two quick links from being connected. And then that allows the redirection of the tension by the parachutes. And we have two of them, but only one of them needs to work for the main parachute to deploy. So some of the specifications of the tender descenders, it's made from treated anodized aluminum. It has a 2,000 pound shock load and a 500 pound maximum release weight. Some important notes about the tender descenders is that they will only undergo the impulse force by the drogue parachute. And because of the way that it works, as you can see there on the first image and the second one, there is no overlap between the drogue and the main parachute. And then to ensure that the E-matches are always connected to the flight computers, we will be using two different wires, one of them being a little stronger, higher gauge to make sure that it doesn't twist as much. But whenever it is released, there's a built-in, I guess, failure mode to ensure that it does disconnect the wires once the tender descenders are triggered. And some other important notes about the tender descenders, we will be using rubber bands to make sure that the middle part is not lost in case both of them work. And that's a little confusing, so I'm gonna run through this example real quick. So in case one of the tender descenders work, the rubber band will tear. And as you can see there on the first row of pictures, if one of them works, the rubber band tears apart and all the parts are recovered. And in case both of them work, only one of the rubber bands will fail and the other one will not tear, and that would allow the two middle quick links to be saved. And lastly, the tender descenders will be covered with a Nomex blanket to prevent it from burning any other hardware. So here's the flight configuration. So the telemetrum is going to trigger the CD3 when apogee is detected, and then 1 second later, the ECME triggers the black powder charge. And then for the main, the telemetrum triggers the first tender descender, and then the second one is triggered a little bit after. Now here is a better depiction of what the recovery system is going to look like. So the first two pictures on the left are the pictures for the drogue. And as you can see there, the drogue, this is not to scale, by the way, the cords are not completely extended. That's just so I could fit it in the picture. But as you can see, once the airframe is separated, the drogue is going to be deployed. And as you can see on that second picture, the tension from the drogue goes through the shortest connection, which is the one by the tender descenders there. And then the main parachute is kept in the bag along with its cord. And then moving on to that second set of pictures, once the tender descender does go off, you can see there those two pictures that are joined together. That's what it's going to look like. I couldn't fit it all in one picture, so I kind of had to work with what I had. And as you can see there, the drogue would be essentially really high up and then would be joined to the main parachute bag. And then the bottom of the main parachute bag would be joined to the top of the main parachute. And then the main parachute would be connected to its cord. And then that would be connected to the U-bolt. And then that picture on the right is what it would look like basically once the main parachute deploys. And here's the flight risk for recovery. Starting off with occasional and negligible is the black powder residue. Now that is something that we're going to try to mitigate with the use of wadding paper and Nomex blanket, but it does happen sometimes. But good thing is that it has no major consequences. Moving on to improbable and moderate is the burn damage to parachute. Again, this is something we're going to try to mitigate with the use of Nomex blanket wherever there's going to be some sort of black powder use. But it would have some consequences on the parachutes and possibly on the descent rate. Sipping of the airframe, that's also moderate and improbable. The reason for that is that the only moment where there's a high risk of sipping is during the initial drogue deployment, but that only has a small impulse force value. And then when the main deploys, the rocket is already vertical, so there's not a high probability of the airframe being yanked from one side to another and sipping the airframe. So a critical and improbable event is the premature misfire. Now that is something that avionics has tested for, so the team is confident that it won't happen. The nose cone cord fails. This cord is rated for 300 pounds. The only possible way that this could fail is if the nose cone is ejected too fast, but again, measures have been taken to make sure that does not occur. And then tender descender parts are lost. Now this would have some consequences on not recovering all parts of the rocket, but with the rubber bands, that should be mitigated. And then lastly, catastrophic and improbable is both systems fell to, both ejection systems fell. Now we have a dissimilar redundant system, and a lot of time and practice has been taken to make sure that all procedures are followed and to ensure that both of the systems are assembled properly. Tender descenders failed to ignite. Again, we've mitigated the risk of any possible failure modes for the tender descenders, whether that being the wires getting disconnected or it not firing correctly. And then main parachute bag gets tangled. The way we're mitigating this is by keeping the cords of the main parachute flaked and held together by a rubber band. So whenever the drogue is deployed and the main parachute is still in the bag, it doesn't it doesn't untangle in the middle of the air, essentially. And then parachute cords fell. Now, we did the analysis on the maximum load on the cords, and with it being 270 pounds and the cords being rated for 1,500 pounds, the team is also confident that that won't be a probable scenario.
All right, thank you, Carlos. That basically concludes all the presentation as far as subsystems go. There are just a few more slides that I want to go over with. And as soon as we're done with that, we can take a 5-minute break and start answering questions. So just maybe a couple more minutes and we'll get started with those. But basically, I just want to go over some key takeaways and a lot of the things we've learned this year. And I guess this always happens every year where we struggle with and is finances. At the beginning of the year, we didn't have enough money to be able to start fabricating, to start buying things. And I guess the biggest thing with being a low budget, low resource team is that we are not able to afford to make a lot of mistakes throughout the whole year. Obviously, making mistakes is how you learn, but whenever you don't have enough funding, it becomes a little more difficult. There was little financial support through sponsorships and so on. However, the team worked very, very hard throughout the whole year in order to be able to raise more fundings. The whole year, especially in the second semester, we started doing more bake sales in the university. We even made a Coachella music concert where we got local bands to play in order to raise money. And also just from donations through a GoFundMe or the SCR members donating throughout the whole year, we're able for us to have enough money to not only build Zenith and go to competition too. And I guess the key takeaways and some things that we have to learn for next year when it comes to finances is things like bake sales and Coachella. To start earlier, right? To start at the beginning of the semester and try to raise more money, to have our more fundraisers, and also help more with the officers. Now, I think we're in a very, very good location when it comes to the relationship between SCR and the IAA. I think next year we're gonna get started strong. We're gonna be able to have a lot more money in order for the team to succeed. And then you can see some of the pictures on the right there. Other key takeaways when it comes to design, testing, and manufacturing, as I previously mentioned, our low resources meant that we had to be 100% sure with our design. If you remember last semester when we started designing Zenith, our whole goal was to get to 30K, and with low resources and not that much experience with making a new rocket, we spent too much time in our design process. There was too many design changes happening throughout the year due to us learning new things or being advised to do different things. It was hard for us to stick with one thing just because we were scared that eventually there will be something better that will come that will help us get to that 30K. And then that obviously led to manufacturing delays. Manufacturing started a lot late, and since we didn't have enough funds, the process was rushed and led to a few issues. And then with testing too, something we've learned this year is that testing should start a lot earlier. And sometimes when you do test things, you might end up failing or things might break. And hopefully next year we can start that earlier. We can mitigate all those problems and come up with solutions and obviously have a lot more funding to be able to resolve those problems. So some, I guess, small changes we want to make for next year is a longer transition period. That way we can have better documentation and able to help the future leads when it comes to recruiting, team budget, event coordination, and meetings. That way those first few months where we spent just trying to get the new members in the team accommodated and be able to learn go by a lot faster. And as I mentioned earlier with the finances, since next year we're not going to be building a brand new rocket from scratch, I think there's going to be a lot money. There's going to be a lot more money. There's going to be less spending. The design process could start earlier and focus more on the specifics of the subsystems. We can probably afford more testing and be able to test more things and have more materials and tools at the lab. And as I mentioned earlier, this is the first time we've built a rocket in a very long time. And we decided to be very ambitious and try to build a rocket to try to go to 30K, something we've never done before. So with our member retention and with all the experience we've gained this year, I think next year we're going to be in a much better spot. But right now, in the next month, our whole goal is to just make those final changes with Zenith and be ready for competition. I think everyone this year is very excited to be back at Space for America Cup for the first time in 3 years. So this will serve as a learning experience, and we are very confident we will be really successful at the competition. Now, just a little bit for next year, our whole goal is to make Zenith a lot more like SRAD and have student research and develop subsystems. So for structures, producing our own frames, making a new boat tail design that makes fin modularity a lot easier, working with composites, recovery, since we had a capstone team working on a mechanical separation system, trying to implement that. Avionics, maybe reimagine the avionics tray and how we see avionics, maybe utilizing more of that space that we have, doing more with our SRAM sensors, and continuing to work with analysis and get that experience when it comes to things like FEA, CFD, and mathematical models, calculations, and so on. Payload, I think next year it's time to make a brand new payload, maybe become even more ambitious than we've had in the past. And then obviously in the next few years, switching to an SRAD engine is kind of what we want to do. But without a lot of funding, it's hard, but I think we're in a really good position for next year to be able to not only get that funding, but because we have the experience. If you do want to help us out with funding, if you just want to keep up more with us and what we do next year, you can send us an email either to me over the remaining of the summer, or also our future project manager, Josephine, or our AIAA treasurer, Arturo. Here is their information. And if you just want to make a donation, if you're watching this right now or looking through the slides or the recording later, those are other options there. We really appreciate everyone helping us out. I guess just you advising us is enough, but we obviously would appreciate a little more help because we do want to be that engineering team at U of H who is able to push boundaries when it comes to what an engineering high-power rocket team can do. And then special thanks right before we take a little break and we come back to the questions are these people. Randy, we're so thankful for you helping us out, always advising us, always being there whenever we have questions. We're so happy to have you. Dr. Zaskan for being our UH faculty advisor and keeping up with us. IA Coatings for our donation support. Zenith is with them right now. And also our alumni advisors who've been with us throughout the whole year when it comes to Zenith. You see these names here, Alex, Emily, Dom, and Eric. Y'all have been amazing to help us out. Everyone who has financially supported us too, and our sub-team leads and members. I'm so proud of every single member that's been part of the team throughout the whole year for just sticking around and working very, very hard. So thank all of y'all and thank everyone who's here. Right now, let's take a 5-minute break. At around 8:55, we can come back and just start answering questions. And so sub-team leads, if y'all can be prepared for that. And yeah, that's that. We'll be back at 8:55. So I'll see you in a couple of minutes. Okay, hello. Oh, can everyone hear me?
I can hear you.
You hear me? Okay. All right. I am looking through the questions right now. Okay. We are ready to start answering questions. So let me see if there are any in the comments, unless somebody wants to go first. Randy, I know you asked a couple. I don't know if you want to ask them right now.
Sure. Well, some of the questions I didn't ask or didn't start typing in until I thought about it.
Okay.
So one's more philosophical. Why do you think you underestimated the time and resources to do your reevaluation of design and all of that work? That's more a project management question than it is highly technical. So what were your lessons learned from doing your scope and man-hour estimates and duration estimates?
So I guess when we started off the year, we just wanted to, we were planning on designing everything. We had a set deadline as to when we plan on manufacturing things. And I guess the mistake when it comes to project management that we had this year is sticking with an idea and then improving upon it.
Unforeseen scope changes. That's the number one killer of every project. So you're not alone. And I wouldn't call it a mistake. It is the nature of our beast that we work in. So that's a very good lesson to learn. So very good.
Also,
Yeah.
that
Go ahead.
spent a whole lot of time at the beginning of the year trying to recruit members for the team and train them up and introduce them to all the concepts that we wanted them to know. And that took a lot more time than we originally planned for.
Yep,
And,
it does.
So
and
yeah, go ahead.
Oh, well, your action item to have a training manual in place, orientation processes in place, that'll all facilitate that. But that's enough on the project management. Y'all caught the key idea, and that is not, if you don't manage your scope will manage you. And we all, even today on the projects I work on, which have multiple schedulers and planners involved in it, we still have the same problem. So y'all are not uncommon. Welcome to engineering.
Thank you. Yeah, it was, there was a lot we've learned this year.
Yep.
So much. It's crazy.
Yep. One comment, y'all need to get a hold of a copy of RAS Arrow and rerun your altitude sims. RAS Arrow has the best CISA-D calculations. From my experiments, okay, so I've sat there and run stuff, and I use my altimetrums, my telemetrum, altimetrums, and so I get the data. So I been comparing the data against the sims, and open rocket, so it's somewhere around 13 to 17% low in altitude, and RAS Arrow actually worked out. Not RAS Arrow usually works out close, and RockSim surprised me at times as being close. So, but it's all in the CISA-D calculation and RAS Arrow. And if you go run your calcs in RAS Arrow and get the CISA-D curve table and put it into RAS Arrow Pro and redo it, you will get, that's where you get your best altitude estimates. So, but it's worth at least running some calcs, some sims on RAS Arrow and look at the altitudes it'll give you.
Okay.
So I did compile all the questions if you guys want me to go through those. But if anybody has any questions they have on the top of their mind, we can answer those while you have them.
Okay, you can go, Goose.
Okay. So the first question was from Randy, and it was, what is the tear out load of the motor retainer?
Do you understand?
Yeah,
okay,
we need explanation.
Okay, so you have your thrust plate is got what, 8 screws, and those 8 screws are going to be handling the load from the or screwed into the wall of the airframe. So there's a tear out load, right? Going back to structural engineering, even though I'm a chemi, I had to take statics and dynamics. So there's a tear out load. Y'all have good spacing, so that helps mitigate the load. But are you familiar with what I'm talking about on when you're in structural, when you look at 2 plates being mounted together and you have tear out loads?
We're not.
Okay. Let's talk about that offline then. But basically, you analyze the stress around each screw to see if the material is strong enough to handle the load. So with 8 and given all your numbers and what G10 fiberglass and the size of the screw and the area around it, blah blah blah, you should be okay. But we'll talk about that in a little. We can talk about that offline.
Okay.
But that's it. That's the important thing. And that's kind of like what y'all did on the fins. And I've got questions about the fins later. So anyways.
Okay. Next question, Goose. Yeah.
Yeah. The next question was, are there shear joints using tensile, or are the shear joints using tensile allowable? Are they using thread root diameter, bolt bending considered? Very concerned you're way undersized. Robbie, I guess it's a question for you.
Yeah, Irvin, if you could go to the, I guess the slide above that, 35. Sure. So we assumed that the shear strength was going to be 60% of the tensile strength. And that was what mainly drove our screw calculator for that allowable screw load that you see, which then gave us a number of screws required. I believe we weren't able to consider bolt bending, but we did use the major diameter of the screw. So
yeah, so you do need to use the root diameter, especially if you had got those the threads in shear.
Exactly.
Okay.
Yeah.
Cool. You can rerun.
And again, you definitely do need to consider bolt bending. That's going to probably going to push your factor safety way down. You might even get kind of a less than 1 safety factor there.
Yeah.
Again, just because you're going into threaded holes, not just going straight through and a nut on the other side. So you're going to have maybe about 1 or 2 threads unsupported in your hole, because those kind of first 2 are probably gonna be a little bit oversized relative to the rest. So you want to assume maybe 2 threads are kind of unsupported, and that'll be your moment arm effectively.
Mhm.
Yep. Yep.
Yeah.
And
I
again,
want to
you'll
add
want to consider the root diameter for your bending section properties as well.
Yes.
I would add to that we probably should run those calculations just to confirm and make sure that we're still within the factor of safety. But we did run this calculator for Oberon whenever we have the shear pins screw. So not shear pins, the plastic rivets shear for our payload bay. And using this same calculator, we concluded that 6 832 screws would have worked for the payload bay, and it worked for our second flight of Oberon. So still worth running the calculations, but I think this is okay for now.
Yeah, there's probably some conservatism in your load. I don't think you're going to get 30,000 pounds on your landing, but definitely, make sure you understand what's going on there. I just put in the chat, NASA STD 5020 is kind of the Bible, basically, of faster analyses, and it'll have all the equations you need for, especially, you really want to check interaction of all those different loading events. So tension, bolt tension, shear, and bending. That spec will have all that for you, so you can go reference that as well.
Okay.
Thank you for that.
The next question is, how are you attaching the fins to the motor tube? Asked by Randy. And yeah.
So is that going to be a tip-to-tip carbon fiber layup?
Yes. So on top of being a tip-to-tip carbon fiber layup, we're also going to start with the chopped fibers of the fiberglass and the epoxy, just so we can get them settled with where we want them first, so we're not worried about them shifting around while we're doing the tip-to-tip layup.
Don't forget to put fillets in before you do the tip-to-tip. So you.
That's what the chopped fibers are going to be for, is for the fillet.
Okay, fine. Good plan.
Okay, next question.
Hey, Gustavo, can I throw a question out that wasn't in the chat?
Absolutely, go ahead.
So since we were talking about bolts, could y'all go over again what those flange nuts were being used for?
Yeah, I got you. The flange nuts were, okay. The flange nuts are going to be used inside the bays, and they're used to secure the bays to the airframes. The flange nuts are epoxied onto the inside diameter, or I guess it's the inside space of the bays, and they're just epoxied in place so they can stay in place. There's not going to be really any load there on the epoxy.
Okay. Yeah, I always have concerns with this sort of setup because I've experienced epoxy breaking on a nut like this and it's spinning. Typically in industry, we use things like nut plates and things like that to mitigate that kind of thing. A lot of times those nut plates will be epoxied in place too, though, but they're meant to be epoxied in place. Did y'all consider using anything like that, like a nut plate, rather than just a nut that's epoxied?
Sort of, but we concluded that just nuts would work fine. We use it as well for the payload bay in Oberon, and that seemed to work fine. So I don't think there's too much of a risk concern here. And yeah.
Okay. Yeah. If y'all have experience doing that and haven't had any failures, I guess that's good enough. But just something to keep in mind. Watch out for that.
Everything. Thanks for the tips.
Yeah, ultimately, as long as so the epoxy is really only going to be used during install, right? All it has to do is react, your torque as you torque down the bolt. So one thing you want to consider here to make sure you do, to make sure that this bolt doesn't, back out or anything. Do these nuts have locking features at all? And are y'all preloading these bolts to a certain amount, or are you just kind of tighten it hand tight and leaving it at that with no additional locking feature?
Yeah, that's correct. No, there's no additional locking feature. We could add Loctite at the launch site, but Loctite.
I would avoid it.
Yeah.
I think I would be concerned if you had an additional locking feature that you'd be more likely to break the epoxy bond with just epoxy in place.
Yeah.
Also,
Yeah, but you kind of still do need something to keep the bolt from backing out.
use a stars lock washer on the nut.
Yeah, that could be a
Nuts.
consideration. We do already have all of our nuts epoxy in place, so we could probably just break those off.
Well,
You don't have to break the nuts off, just use a lock washer on your bolts.
Yeah, but the lock washer would be on the outside surface of the airframe.
Okay, fine.
Okay, noted.
I know that in the past we tried to find out the braking torque of epoxy nuts. I believe that was a long time ago. Some of Ravi's help structures. I'm not sure if I have any of that data.
Also remember that y'all have available to you from Da Vinci Labs is a treatment for the aluminum so that it can be epoxy to with about the same strength as a weld through their patented technology.
Is this to an aluminum airframe? I thought it was a fiberglass airframe.
Doesn't matter. It's a treatment on the aluminum that gives it bonding to the epoxy and to the fiberglass as strong as a weld would be. It's amazing stuff.
These are going to be stainless steel nuts, though.
Doesn't matter. You still have aluminum, so it'll hold. The aluminum will hold on to the epoxy better.
These were epoxy to the airframe, which is
Oh, okay. To the fiberglass.
Right.
Okay, fine.
Still might not be a bad idea to use nut plates though. You'll get a little bit more surface area for contact, so you can feel a little bit comfortable that way. Or you can use alternatively riveted on nut plates instead of epoxied. Whatever makes you all feel more comfortable. But that way, and also you get the benefit too. A lot of these nut plates you can get kind of floating nuts in like a cage, so you won't have to worry necessarily about perfect alignment of your nut relative to the airframe, because your nut's floating, so you can have a little bit of compliance there too. So that might just make things just a little bit easier.
Yeah, I will always upvote nut plates. You can find them on McMaster car. Probably that's what Eric just linked. Anyway, I'm good.
Yeah, those are all great tips. Thank you, guys.
Thank you. Next question. Goose.
Next question is from Randy. He was asking for a clarification on acceleration versus pressure on the avionic sensors for payload.
Yeah, I mean it may just be a word usage. Are you talking about barometric pressure changes, and actual pressure, flight pressures, or are you talking about accelerations, G's? When you were talking, it was on the actually it was on the biological payload.
Payload slides.
Yes, I'm sorry. I was using acceleration forces and pressures interchangeably just because they're very closely related. Acceleration and pressure are both measured by the avionics sensors. We're looking at how accelerated forces affect E. coli as it would the human body.
I understand that, and I understand acceleration can be turned into pressure, but they're not the same thing. So you need to keep your nomenclature straight.
Okay. The next question is, why is the charging cable fall out of the plug? What is the mitigation? I guess the question is more, what is
okay? So on your risk, you said it's improbable that the power cable can fall out. I have firsthand experience with that happening on a rocket, even after I thought I took great care to prevent that from happening. So what mitigation steps have you taken to ensure that the plugs won't fall out?
The mitigation would be a charging lock. We have decided to either buy one or form one out of zip ties and wrap them around the cable as well as the power bank.
Okay, so that would have been the mitigation, but it's not improbable. It's likely. It happens all the time, and it's in between occasional and likely. on how often it happens. I've even had wires break on takeoff. I have firsthand pain on that, where I thought I had everything tied down good enough and it still came loose. And so I flunked my first L3 flight because of that. So yeah, a lot of things y'all are calling unlikely or not unlikely, improbable, have happened numerous times. In fact, we had a ballistic return on a L1 flight this last weekend, because the ejection charge didn't work right. So it's not improbable. If it's happened in the industry, it's not improbable. It's either seldom or occasional or likely. Y'all are underestimating your risks.
I guess this is the question for you and all the alumni is, I guess the way or ideology when it comes to our risks and risk matrix, it is, if something is in the red, that means we're not ready to launch.
No, that doesn't mean that from my industrial experience. It means it's something you have to mitigate. So this risk chart, as I'm used to seeing it in my industry, and somebody may have other experiences, and that's fine. But in my thing, this is the unmitigated risk is what you're going to talk about first. Then you talk about how you're going to mitigate it to lower the risk from likely to seldom.
Okay.
But it's, do not paint a rosy picture or you will fool yourself into a bad day.
I think part of the reason that we ended up doing that was initially we did have some things in red. This is back during the PDR, but then we had some alumni come forward who pretty much told us that we shouldn't have anything in the red, and that we've had things in the red, then we weren't good to fly and we had to change things. And so I think that's where some of that miscommunication ended up falling in, was we had heard different reasonings for the risk matrix.
Okay.
So I think we agree with what you're saying of like, we need to acknowledge them and like where they should, that we can have things in the red if it's going to happen. So I think that matches our initial thought.
No, you see, Haley, you're making perfectly good sense here. So you say risks, unmitigated risks. Then tell me what the risk is after you apply your mitigation, and tell me what your mitigation is. We're always going to have risks, and we are always going to have risks that are in the red. But then we figure out how we are going to mitigate them, just like you described. That was exactly a perfect explanation. It's just a matter of presentation.
Yeah, and just to clarify too a little bit, it's also important to keep in mind the stage of the presentation that we're given. In industry, if you're going into a flight readiness review, you're on the launch pad, you're basically ready to go. So if you have some unmitigated catastrophic risk, something in the red, that's a big red flag. You stop, right?
But you just said the key word, unmitigated. Right. And so again, you need to present what the unmitigated risks were and what the mitigated risk is for these.
Right. And
I
just,
think what
just
the
to
alumni
add on to,
smart.
Sorry.
We're all answering the same question. I think.
Yeah, we're saying the same thing, guys. We agree.
Yeah, the original alumni comment was that you can't leave anything in the red.
That's right.
You can't leave it if you don't have a mitigation plan. And I think what we didn't see at the beginning was a plan to mitigate the risks. And so if you have stuff in the red without any way of addressing it, I think that is what the concern that we brought up. And so now we're seeing things not in the red, but we still don't see how those things have been mitigated.
Yeah, we don't see why.
And that's the other part, that's you need to tell the story of how you got from higher risk to lower risk.
And something you can do for next year too, as you essentially, the way these risk mitigations go typically is that earlier on in the program you'll have most of your risks and there'll be a lot of red, and as you kind of develop and mature the system, you'll start going through your mitigation plan and burning down some of these risks. And there is kind of like a waterfall chart that's typically used to kind of show the plan ahead of time of how these risks are going to be mitigated with tests or whatever. And then as you mature the system, you kind of go through the waterfall and you show how you're burning down risk and, you know, through the life of the program. So yeah, you're not just going to present one, you know, risk matrix throughout the whole program. You got to keep in mind where you're at in your maturity too.
I highly recommend when y'all are addressing risks, talking about risks like system level risks, go look up NASA resources for systems engineering. NASA has several handbooks that are all about systems engineering and risk management that have a lot of good processes for doing exactly what Andrew just said.
Great
All
ideas,
open to
guys.
public.
Excellent.
Thank you. Yeah, I guess the way we've been looking at these risk matrices is just for the presentation. We haven't really like done it throughout, like, let's say the CDR, then a PDR, or sorry, other way around, and trying to like mitigate those issues. It's just been like, oh, here are our risks, and here's what I think they are at the moment. So that's great. Thank you for the feedback. We can go to go to the next question.
So the next question was, what are your payload contamination mitigation strategies?
So regarding contamination mitigation, we're handling everything with proper PPE. So masks, gloves, sanitizing everything, lab coats. Another thing we're doing is spraying equipment in the bay with microban, which is designed to continuously kill bacteria for up to 24 hours. Also, the commensal E. coli that was chosen was confirmed to not cause infections, as it is a harmless strain listed by where we got it from, but it will be contained in a sterile petri dish that's confirmed to be airtight and has a very high chemical stability. Another extra step we'll take is wrapping it in clean wrap and also covering that clean wrap in microscope tape, which ensures that it shuts and blocks all of the bacteria from coming out.
Will do. Any questions on that? Okay. The next question was, somebody asked that they didn't see any mitigation for any of the cases, and if we can confirm if they're defined somewhere in the report.
I think we kind of just went over that, so I think I'm good with that. As long as y'all, you know, just take that feedback and probably use it for next semester. And go read. Michael just linked the basically the Systems Engineering Holy Bible as well. So
Yeah. Okay. I guess one thing worth noting is I think some of us did end up defining the mitigations whenever we were doing our risk matrices for the PDR. Like I know that structures has a whole separate folder for it, but I guess something that we just didn't include in here, but they are defined in our drive. If you did want us to like send those for like confirmation that we like actually kind of understand it a little bit more if you're curious.
That'll be very useful, but the other place you need to have that mitigation strategies available is whenever you're at the question and answer session at Spaceport America. And I talked to Gustavo about having a book with all your specs, data sheets and stuff, and the mitigation plans would also be in there. So if any of the judges start asking you about why can you say this, anyone can go open it up and find it and talk about it so that y'all look really bright like y'all are.
Any more comments on that? Okay, I'll go on to the next question. Somebody asked, PLA would not melt, but did the payload team account for any potential deformations that could occur as a temperature of the environment? Okay, the question's worded a little weird, but are there any external supports to prevent the deformation?
So there are no external supports. The payload team went through a series of heat chamber testing where we tested PLA at temperatures up to 200. The, I guess, temperature it starts to warp at is 111 under like glass transition. We are mitigating a lot of heat so that the GoPro as well as the power bank don't overheat. So we're with the cooling system, we're aiming to keep the bay under 100 degrees. Another thing we did was compare our current temperatures to the temperatures that were recorded within the payload bay from last year. And the temperatures inside the bay were lower than the external temperatures because fiberglass is an insulator, so it neglects, I guess, the greenhouse effect.
Okay, thank you.
Hey, so just to add to that, so when you did your testing, did you do it under any sort of load, or was it just, sticking your PLA at, in the heat chamber and that's it?
We just stuck our PLA in the heat chamber.
Okay, I recommend, because even though you might not necessarily melt or go through the glass transition temperature, it's going to soften. So if you take whatever supported weight you've got on your PLA and then just multiply it by your G load, well, it's going to be higher because it's not just your G load from flight, it's going to be G load from vibration. You're going to get a much higher load under a much not as stiff material, so you're probably going to deform more than you expect just by kind of having a static unloaded part in your heat chamber. And I guess I noticed if these are on your optics, you're going to be probably very sensitive to any kind of deformation, whether it's temperature related or just mechanical vibration or whatnot. You really want your optics to be stiff, otherwise everything's just going to be out of focus, right?
Mm-hmm. Thank you. Yeah, another thing we're looking into is because we have to epoxy our lenses within their mounts, we're looking to coat the PLA in kind of an epoxy resin to strengthen it.
You might even consider, machining something. This is probably something that's good to do a little bit of analysis beforehand, because you're going to be more sensitive to stiffness rather than strength. Because like I said, even if you don't have a structural failure, you might have a functional failure of your optics. So we want to make sure you have not just enough strength, but enough stiffness at temperature.
Also, I'm curious, what plastics did you test aside from PLA?
We tested PLA. We also looked into PCB, PTEG. I have the trade study up.
Well, we didn't actually physically test the rest, right? We just did a trace study.
Mm-hmm.
So the only one we tested was PLA.
Have you tested or considered ABS?
We have not tested it, but Izzy, have you all considered that?
We looked into ABS. I think one of the reasons we went with PLA instead of it was because we were under strict budget at the time, so PLA was a lot more affordable.
I would recommend, if you have the ability to try to test with ABS. I do have some filament as leftover ABS filament if you do need that for testing. Otherwise, I would recommend it as it has a higher temperature capability, being able to function in a higher temperature than PLA, which would be helpful in the case of sending this off to competition in New Mexico.
Yeah, just to voice support of Javier, ABS is much better from a temperature resistance standpoint.
I've personal experience, not really a test or anything like that, but I've had PLA parts just melt in a hot car.
Same.
And just deform.
Same. PLA does not bode well with that temperature. Even in Texas alone, leave it out in the sun for a little while and it will melt, and it will not melt, but it will soften, and then the functionality will not go out as planned.
And I guess kind of while we're on this, can you go back to the chart where you show the drawings for your optics and then that PLA part? Thinking about this too, you see, is there a reason why there's kind of that gap between those two plates? Is there any way that could be closed? Because that could probably help your kind of your stiffness issue here by supporting all of that structure.
Which plates exactly? I'm sorry.
Sorry, it's yeah, that picture right there. You kind of have you got those two plates there and you got that gap. So I could see that, you know, those two parts kind of vibrating like a drum almost and kind of deforming axially relative to each other, and that's going to throw off your optics. So if you were to say, you know, close that, you know, that you might have a better chance of just really, you know, tightening in those deformations.
Yeah, we had that originally just because there was no other way to fit the lens within that without making two halves first. We planned on gluing it together.
Oh, you don't necessarily need to, I guess what I mean, you don't necessarily need to physically, you know, have one piece, you know, just close that gap there. So that way you're not kind of vibrating like a drum. You know, just make the parts thicker essentially.
So would you suggest instead of having like, I guess, the 2 or 4 pillars that connect the two things together, the two plates, fill it in so that only the lens volume would not be filled in by the PLA? Because there would be a lens in between those two plates.
Yeah, that would certainly help. It's really hard to say without necessarily knowing your constraints on what you can do. Okay. But yeah, that would probably help as well. You know, just getting you'd be really stiffening up those plates from bending, and that's something you can throw into FEA and get some actual deformations that way as well.
Is that the thickness of the lens? Sort of the distance between that lower lip and the top of this piece?
Yes.
Okay.
Yeah, so just to comment, I don't exactly know your constraints here, but just be aware of the stiffness of this and make sure that your optics are not going to be, you know, thrown off by flight loads.
I have a question about the picture on the top right. I don't know exactly what that is, but I see that it's on like 4 like long piece. I can see like seems like 3D printed pieces. Do you plan on printing those? The kind of legs are underneath there, or is that going to be something else?
So this was because we reused the mount for the GoPro and for the macro lens. That was just a screenshot from the CAD for that. Those 4 pillars won't be there because the distance between the macro lens to the 40 times lens will be much shorter, so they're practically stacked on top of each other.
Gotcha. All right.
Any other questions on that?
Yeah, I have a quick question. So I know y'all are gonna keep a power bank plugged into the GoPro while it's flying, right? So have y'all checked to make sure you're able to like actually open that little door to access the charge port for that enclosure? Like the enclosure is not going to get in the way of that.
The closure is not going to get in the way of that. We have space on top of the mount for the GoPro that the power bank will be mounted to, and then the cord will feed just through like the space within the mount.
Okay, cool. And then also, have y'all like actually tried to capture any footage on the GoPro while having it like charging?
Yes, we have. We were running more battery capacity tests just because we got the newer GoPro this week. We ran it. It was lasting up to 4 hours. And then with the power bank, expected with heat, it's to mitigate like, I guess, battery capacity failure. It's been running very well. Another mitigation we were thinking about is if video takes up too much power and overheats it too fast, we'll do a time lapse instead.
Okay, yeah, I just want to make sure that y'all weren't going to run into any issues with that, because I know in my experience, GoPros can act weird sometimes. And if you have like that door open and you're charging it while recording, like, I don't know if you would have like run into any issues with that. So it's good that y'all checked it beforehand.
Alex. Any last questions?
I got some more questions. I got a whole bunch, but since we're on payload, I want to ask these. I know you talked about being able to, well, what contamination things were done to mitigate that risk, but are there any other provisions needed to handle that bacteria, or the E. coli, in terms of not allowing it to die, or other things that you'll be able to have at spaceport or in the hotel when you guys are staying over there?
Yeah, so I have multiple orders of the same strain. The way that it is they're freeze dried, so they're preserved, and like the DNA is frozen. Once you rehydrate it is when they begin living and growing again, and you have to swab them to create a culture, and that culture will be timed until it needs to be used and observed. The agar plate on it is nutrient, so it has a sucrose that the E. coli feeds off of. E. coli doesn't take too much to survive. It's very temperature resistant. It doesn't need oxygen, and it only needs like a simple salt or sugar.
Gotcha. Okay. And have you guys done any? It seems like you just got the GoPro recently, but I think Alex also kind of noted toward this, but seeing how the lens reacts under any vibration, and do we have any vibration data in terms of accelerometers from Oberon at all to have an understanding of what accelerations that the rocket will see in the X and Y, or I guess more Y and Z, to see if the GoPro can even do that under the microscopes that we're putting under there, or the lenses more so?
I can touch on the vibrations question. No, we don't have any data. We have tried in the past to collect data on that, but it's all either been faulty data due to technical problems or just not good data.
Gotcha. And maybe it's a question for Randy. Randy, have you noticed, has this been, I'm sure this data has been captured somewhere for generally high power rockets that go within certain Mach numbers along with altitudes. I'm sure.
That's in the sims. So if you go back through, your max sim number was 14 Gs.
Well, I guess what I'm referring to is the not the axial load in terms of Gs, but vibration and the I guess what we commonly know as X and Y, to see if the camera can keep focus while being shaken around. Or do high power rockets sustain a lot of vibration in the X and Y axis?
Yes, they do. They have vibration, but we fly GoPros or lesser variants of those guys all the time. And for what we're doing, which is mostly wide angle, it's fine. And you don't see any noticeable vibrating in the rocket. You may, with the way we're looking at the way they're using it as a microscope, that's not something, this will be a first time I've seen this application used. So rigidity is going to be important just to keep things aligned, as y'all questioned. And then concern over deformation due to the high G loading is the other concern, because you're exactly right. If the mounts sit there and yield under the 14 Gs, they're going to go out of focus and you won't see anything. So that would have been an area for some ground testing before flight testing. And time is short now.
Any more questions on payload?
I have just one quick one. I know you mentioned you had included ballast on your payload. So you are just to make sure you're still consistent with the rules on, I can't remember exactly the percentages, but there's only a certain percentage of your total payload mass that's allowed to be ballast, right? I'm not sure if that's rules change. Okay, thanks.
Yeah.
I had a really quick question about structures. Whenever you guys are going to epoxy the fins, do y'all have some sort of plan on how you're gonna keep the fins like perfectly aligned while they cure and stuff?
Yes. Okay. So the plan for that is we already have the dimensions of the motor sleeve and of the thickness of the fins, and we're gonna print two 3D guides to keep them straight with each other, and then we're going to do that fillet on them. We're gonna let it dry with the actual guides on it, and then we'll pull those guides away, and that's when we'll do the tip-to-tip layup.
Cool, that's perfect. That's exactly what I was gonna suggest, like some sort of 3D printed jig or something. So just making sure.
Hey, while we're on this fins and structures on this page, I got a few questions if y'all don't mind. I guess first of all, I remember previous iterations of this thrust structure. I was a little concerned that it looked like the fins were kind of in the load path of the motor. Is that still the case here, or are these fins not taking any thrust loads?
So it should actually be the centering rings that's taking the thrust load, not the fins themselves. But they are on the motor sleeve. So if that's where the uncertainty was.
Yeah, I think that's really where the uncertainty is, because the loads are really going to follow the stiffest load path. So if you make your fins too stiff and they start picking up load, you might be concerned that they're just going to start to buckle. And you don't really want the fins taking load. It's probably not going to happen, just given things are pretty low load here and your fins seem pretty stout, but that's something to check, I think.
So I think one of the things that we also have is the FBA that analysis has been working on, where we're trying to see where that load is being distributed. So from that, we're also checking like how much load the centering rings, motor sleeve, the fins would be taking, or how much deformation would happen, which is helping us decide whether the motor sleeve is taking any load. So I think using that, we're determining that it shouldn't be taking any of the load, especially since the centering rings aren't actually, well, the bottom centering ring is in contact with the fins, but it's not actually giving load to the fins. Okay. Or it's not giving a substantial load to the fins where it needs to become a concern.
Okay, we got to remember this rocket, we're not using the motor tube for retainage. All the retainage is being done by the thrust plate, and that's taking all the load. This is basically floating.
Gotcha. So there's a thrust plate taking the load straight to the skin then?
Yes, straight into the airframe. Right, Haley?
Gotcha.
Okay, so it's going straight into the motor sleeve. The motor sleeve sits completely flush over the actual motor tube.
Right.
I don't have a picture of it anywhere in here, but there's not, I guess, an actual thrust plate per se, but yes, it's being all completely transferred into the motor sleeve.
Well, no, you've got the plate at the top with the 8 bolts in it. That's tight.
The motor
and the motor is rigidly mounted to that plate.
Okay, I think there's some confusion here. Let's see if we can clarify, because it is confusing even when we're explaining it to our members.
Can you pull up the overview?
Yeah, so I'm going to right now. Let me see.
Okay. So the way that this, I guess, motor thrust and retention system would work is the motor we're using is an 03400, and it is using Cicerone, I guess, 98 millimeter hardware. And
right. But that's not relevant. Everything that's relevant is where the motor is attached. You have no motor retainer on the rear edge of the motor of the tube.
It is important, and I'll explain why. The thrust ring on the motor is also the aft closure for the motor, and that has I don't remember the exact measurement, but it's like a 0.025.
It's like a 0.01. It's like a 1/10 of an inch to two tenths of an inch.
It has a
So
lip.
that's up against the motor tube, right?
That thrust ring would push against the motor tube, which is highlighted in almost like a greenish color.
Yeah.
And that is like basically against the, it's like a sleeve around the motor tube, the motor piece.
Right. But the front bulkhead is
Will not-
rigidly bolted to the plate up here at the front,
Correct.
the red plate.
The forward closure for the Cicerone motor will be bolted to the motor retainer at the top of the motor.
Right. And so
That-
you're going to, when you screw this, when you mount the motor inside of here, you're going to, at the rear, you're going to sit there and twist the motor until it tightens down onto, you have it tight, right? So you put a slight load onto the motor tube. But when it comes to all the thrust, when this motor expands due to thermal and pressure, because the front closure is not floating, it's in direct contact with that ring. That ring is taking all the load.
No, in fact, we're designing it such that there is a gap between, a 1/4 inch gap between the forward closure of the motor and the retaining ring.
But the bolt's going to be rigidly attached. It's all going into the bolt.
It's going to be rigidly attached in tension. So there's nothing supporting any thrust being transferred through to the motor retainer ring. It is just a through bolt that, once tightened down in tension, will apply to the motor.
That's what your FEMA shows.
Sorry, I'm going
I
to
think
it right now.
we for the MLA FEA, we didn't incorporate the top motor block into that.
Then y'all need to go back and redo it with that with all of that taken into account. You've missed a major issue, a major part.
Randy, I think this is more of a visual thing, because there wouldn't be any load being transferred the way we have it designed. And I apologize for not having a better figure on that.
Yeah, I think we got to show you with more figures. Yeah, I think this is not representing exactly how it's going to be distributed.
Okay, so if the rear closure is up against the motor tube tightly, right? And you have the bolt in tension, the question becomes, as the motor heats up, the casing expands linearly and grows in length. It also grows from the pressure. Since you've got it tied at 2 points, the only way it can move is either to push through the plate or push out the back. Mother Nature is really rigid on this point.
Yes.
Because the fiberglass isn't going to stretch.
Yes. Once again, the motor retainer ring is designed in such a way to where there is a gap and there wouldn't be any force.
It's the threaded bolt that's going to be taking the load.
Correct, but the threaded bolt does not have anything retaining it to the ring. It could push through without any load of.
Okay, there's no threads in the ring that the bolt threads into. It's just stuck up there.
Yes.
How's it not falling out? How does the motor not fall out?
Actually, Carlos, because you're in the lab, can you grab the motor block? It should be on the shelf on the left side, probably like 3rd drawer.
I think I follow. So you have a bolt at the top that you're pre-tensioning to keep it there while it's static, but if it grows, you're just going to lose all of your preload essentially immediately.
Exactly.
Can we go to the picture of the motor block, please?
All right, here we go.
Okay, so essentially you can see this little divot right here. There's no threads in the actual motor block. You just have the countersunk bolt that's just sitting in there. So while it is keeping the motor from falling down, if it pushes up, the bolt just pushes up with it. There's nothing keeping it from going up.
Okay,
That's what's
that wasn't
keeping.
clear. Okay, so thank you for
I'm
that.
sorry, I did mean to explain more, but I guess I was just trying to rush through the presentation because I knew we had a lot to get through.
Right. So this is floating, so it can push forward. So all the thrust is going into the motor tube, into the two fin rings to transfer the load into the airframe.
Yes,
Correct.
yes, sir.
Okay.
Yeah, I'm sorry that wasn't clear. I was trying to clarify.
No, that was not
but-
clear because when I was looking at the picture of the ring, it wasn't clear that there was or was not threads in it. And what I'm used to seeing is we normally thread it in the top, and that's where we put all the load into.
Yeah, that's my bad. It's clarified a lot better in the tech report, but for the slides, I wasn't sure how in detail to go.
So are y'all controlling the preload that you put on that bolt? Because if you put in too much, you're gonna A, start bending that plate, and B, you might not relieve as much. You might not relieve all that preload that you're trying to do, and you might still be passing load through the bolt, right?
Well, if there's not a bolt on the bottom side, if the top of the bulkhead doesn't push into the plate, it can't happen. If there's no bolt on the back on the bottom side of the plate, it can't happen. If there's only a bolt at the top, my next concern becomes, how are you going to keep that bolt from how are you going to keep the bolt and the nut from coming loose in flight? Because that motor will rotate from the vibration. And it has been known for motors to become to unscrew themselves, and as soon as the thrust ends, the motor falls out.
So I know that one idea that we had for as far as stopping rotation was to epoxy something to the actual bolt to keep it from actually spinning. No.
That's not the worry. The worry is dropping the motor out once the thrust stops. That's what I'm worried about. So double nut it and put a lock washer between the two nuts at the top on the top side.
Is this bolt going into the motor casing?
Yes. It goes into the forward closure.
Can you just use Loctite on the threads that are going into the motor casing?
You don't want to put you put a nut on it with a lock washer.
You might even just want to go with
and you're saying that
wire.
can just sorry, go ahead.
Sorry. You might also think about a lock wire too at the top end. Well, actually no, because that's floating, so that might not be a good idea.
Right, but if you double nut it with a lock washer between the two nuts on the forward side of the plate, and then up against the bulkhead, you put a lock washer with a bolt that holds it to the plate, because that motor casing is an $800 item. And if you put thread lock in there, even if it is the blue, it's going to get hot enough that it could actually cause the thread lock to come loose. Because that thing gets hot, very hot. So nothing wrong with the design, just you need to double nut and put lock washers in there.
I guess you also might want to be careful. So if you're going to do that, are you going to start, you probably want to start preloading the nuts, the double nuts too, instead of the bolt.
Right.
And you might start loading up the plate that you don't want to do.
Yeah,
especially with that gap there.
Yeah.
Is there a reason y'all just, didn't do, bolts through the skin or something, just so you have it, just a shear joint there to keep it from moving?
Well, if the motor rotates, it's not a big deal in reality. The only problem is unthreading.
Yeah. Here is I guess a CAD representation. This is
that's very good that you got that. Excellent.
This is a preliminary one. Doesn't have all the detail involved, but as you can see, this is just representative of that plate, and we have the bolt here. It's free to flow move forward, but obviously the bottom face of the bolt was what would be having it in motion and keep retaining the motor.
Yeah, I think everyone's worried about that bolt coming loose from the motor.
Correct. Yeah.
So put a lock washer and a bolt against the forward closure, and then double nut the top side with a lock washer, and you'll be fine.
You don't think Loctite will help, Randy?
I don't put you could use Loctite on the nuts, but if you do anything in Loctite blue, you're going to have trouble getting it apart afterwards.
Mm.
And lock washers work fine. They've worked fine for a long time before thread lock came along.
Mm-hmm.
But on the forward closure, you don't want to use Loctite, because if you galled up the threads in the forward closure, you can throw it away. And that's
And
about
also,
$200 or $300 to replace.
is that bolt also, is it fully threaded or is it have a shank on it?
Yeah, that I don't know.
Sorry, I wasn't sure if I was muted or not. Fully threaded.
Yeah, cool.
Okay. It might be, well, maybe this is just more of a nitpick, but it might be worth doing if you're expecting it to slide like that. Maybe you want something like maybe something a little smoother, like a shank bolt, especially if you're not going to use all those threads.
Absolutely, yeah. We'll look
Good point.
I know we're kind of past our time already, but just to give my last my overall comments, I think y'all's analysis and validation this year is more thorough than ever. So I'm really happy about that. Y'all did a good job there. But in terms of flight readiness, I know y'all haven't gotten to this point yet because y'all are still finishing up the rocket, but I want to make sure that y'all aren't neglecting the actual launch procedures. I want to make sure that you guys have some sort of procedure in place for all the pre-launch stuff that y'all have to do. Practice using that procedure in dry runs, and then make edits according to all the issues that you run into the first time, and then practice it again until you've pretty much perfected your procedure, so that you can almost like mindlessly follow it without even having to think.
Mm-hmm.
That to me is really important to the success of this entire thing. So
yeah, absolutely. I completely agree with you there, Alex. And it's a little frustrating that we don't have a rocket done yet, so we can start doing that. But we do have something, or I guess pre-flight checklists in place with everything that we could think of beforehand, labeled out and written out, so we can get those done. But you're absolutely right that if we can get some dry runs in that's going to help significantly with that process.
Yeah, and I think Gustavo and I are fully aware of like the amount of time we have left. It's just 3 weeks basically before competition starts. And as soon as we get everything back from IA, we are gonna practice many dry runs. We already have a pre-flight checklist, but we still haven't, I guess, practiced actually assembling the rocket and everything. But yeah, thank you for the advice. We're gonna make sure that as soon as we get everything, we just start practicing and ensure that everything goes by smoothly by the time we get to competition. But yeah, it is 9:57, so it's pretty late. Always this PDR, CDRs, and FRRs go on for a very long time just because there's so many things to cover. But I do want to thank everyone who joined today and gave us so much feedback. I've learned so much. I think we were talking on the sub-team leads chat, just saying like, oh my God, we got to look this up. So we're going to rewatch this recording and try to fix whatever issues we have left. Obviously finish the MLA, and like Alex mentioned, have our pre-flight checklists and RF assembly process fully down by the time competition comes. I also want to say that I guess in the past and over the last few years, we haven't been the best with keeping up with alumni. But Haley, who's going to be president next year, as well as a future project manager, Josephine, they're going to be working hard on like keeping up more with y'all, sending more emails, showing out all the progress we're making and so on, because this has been amazing. I think we're all very thankful to get all this feedback. And I guess next time you're going to hear from us is in a few days. I'll be sending out a follow-up email with the slides, putting the tech report again, and just, I guess, some notes and some things that we have. I know a few of y'all say you have some questions that you want to ask. You can either send them to me from the email sent the invitation, or send it out to the AIAA email that y'all saw on the chat. And then obviously, when competition comes around, there'll be a lot more things to show. And I guess you can. One
thing to add. In the email that we're sending out next week, we're also going to include something asking if anyone is interested in, like, anyone at their job or anything who is interested in like any sponsorships, advice for sponsorships. I know y'all were saying something in the chat of something that we would be able to do with y'all for like how much time you spend with us. So we're going to send out like a reminder in that email as well. And please respond to it if you have any advice of as far as fundraising, or people who would be interested in coming to a general meeting as a guest speaker, because I asked Irvin to include in the email as well.
Thanks, y'all. I just want to say y'all did a really great job. I think this is, every time I see one of y'all's reviews, it just gets more and more impressive. So super proud to see where the team's going. I do want to say, like, I think that me and some of the other alumni do feel a little bit underutilized. I don't think I've heard from any of y'all in probably 6 months or so. And I think that's a big reason why these meetings tend to run really long, because I think, we do have a lot of inputs. We do have a lot to say. So I think involve us early, involve us as much as, you want. I think a lot of us are really willing to help out and give these inputs whenever. So just remember that, and, just reach out to us more.
Sounds good. Thank you so much. All right, I will stop the recording right now.